What if the very first moment of the universe was also its last? What if the Big Bang, the event we point to as the beginning of everything, wasn't a singular, linear starting point at all, but merely one beat in an endless, cosmic rhythm? This isn't just science fiction. It's a frontier of cosmology that challenges our most fundamental understanding of time, existence, and reality itself. We are about to embark on a journey to explore one of the most profound and mind-bending ideas in all of science, the possibility that our universe is caught in a cosmological time loop. This is the concept that the cosmos might not have a true beginning or end, but instead cycles through birth, death, and rebirth in an eternal return, a grand cosmic heartbeat echoing across eternity. For centuries, humanity has looked to the stars and wondered about our origins. We crafted stories of creation, from gods and giants to a single, definitive moment of Genesis. Modern science gave us the Big Bang Theory, a powerful and elegant explanation that has become the cornerstone of our cosmic history. But what came before? The equations of general relativity famously break down at the moment of the Big Bang, at a point of infinite density and temperature known as a singularity. It's as if the cosmic record skips, leaving us with a profound silence about the ultimate why and how. This silence is where the most daring theoretical physics begins, venturing into realms where time itself may behave in ways our everyday minds can scarcely comprehend. We are going to dive deep into this mystery, examining 30 of the most fascinating theories that attempt to describe the universe's potential first cycles. So prepare to have your perception of reality stretched. We will explore concepts like the Big Bounce, where a previous universe collapses in a big crunch only to rebound in a new Big Bang. We'll consider the implications of eternal inflation, where our universe is just one bubble in an endless, frothing multiverse. We'll even venture into the strange world of conformal cyclic cosmology, where the distant heat-death end of our universe becomes mathematically identical to a new high-energy beginning. This is more than a list of ideas. It is an invitation to step outside of time as we know it and to ponder the ultimate nature of existence. This is the story of the universe's first time loops, and it is a journey that begins not with a bang, but with a question that echoes across the ages. Our journey into the cosmos's deepest rhythms begins with a theory as elegant as it is radical, proposed by one of the most brilliant minds in physics, Sir Roger Penrose. His concept is called Conformal Cyclic Cosmology, and it paints a picture of eternity that is both beautiful and profoundly strange. Penrose asks us to consider a universe without a true death. In the far, far future, trillions upon trillions of years from now, our cosmos will have expanded to a state of near nothingness. Stars will have long since burned out, black holes will have evaporated, and all that will remain is a thin sea of radiation and fundamental particles spread across an unimaginably vast and cold emptiness. This is the heat death, the end of everything as we typically envision it. But Penrose sees not an end but a transformation. He uses a mathematical principle known as conformal geometry, which is a way of rescaling the universe. Think of it like taking a map of the entire world, and instead of throwing it away when the journey is over, you shrink it down to the size of a single point. From that point, you can then create an entirely new map for a new journey. In this cosmic rescaling, the infinite vastness and endless time of a dead universe are mathematically equivalent to the incredibly hot, dense, and small singularity of a Big Bang. The end of one universal cycle, or what Penrose calls an eon, becomes the beginning of the next. In this model, there is no definitive first cause because the chain of eons stretches infinitely into the past and the future. Each cycle births the next in an endless loop where the final state and the initial state are one and the same. The most controversial and fascinating part of this theory is the potential for evidence. Penrose and his colleagues suggest that if a previous eon existed, some trace of it might be imprinted on the very oldest light we can see, the cosmic microwave background radiation. This is the faint afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. Within this fossilized light, Penrose claims to have found anomalies, concentric circles of slightly warmer temperature. He calls these Hawking points, named after his friend and colleague Stephen Hawking. The idea is that these points are the final bursts of energy from supermassive black holes that evaporated at the end of the previous aeon. Their immense gravitational waves, ripples in spacetime itself, would have carried through the transition, leaving faint circular ripples in the fabric of our own universe's birth. This claim is hotly debated within the cosmology community, with many scientists proposing alternative, more conventional explanations for the patterns. Yet, the mere possibility that we could be holding a fossil from a universe that existed before our own is a staggering thought, one that challenges the very linearity of history. While Penrose's vision stretches across eons, another compelling theory brings the cosmic cycle much closer to home, operating within the intricate framework of string theory. This is the ekpyrotic and cyclic model, a concept that replaces the traditional Big Bang with an event of immense yet controlled collision. The name itself, ekpyrotic, comes from the ancient Greek for conflagration or great fire, hinting at the explosive nature of its proposed genesis. Instead of a universe exploding from a single, incomprehensible point, this model suggests our entire cosmos exists as a three-dimensional membrane or brane floating within a higher dimensional space. We are not just in a universe, we are a universe, a vast flat sheet of reality adrift in a grander cosmic ocean. Imagine our universe as one slice of bread in a cosmic loaf. Parallel to us, just a tiny distance away in an unseen dimension, floats another brane, another universe. For most of the cycle, these two branes are slowly drifting apart, pulled by a mysterious repulsive force that we might identify as dark energy. As they separate, our universe expands and cools, much as we observe today. But the cycle doesn't end in eternal separation. The theory proposes that the branes are eventually drawn back together by an attractive force, perhaps through invisible strings connecting them across the bulk of higher dimensional space. They don't just gently touch, they collide, and it is this colossal, universe-spanning collision that we experience as the Big Bang. The immense kinetic energy of the impact is converted into the searing heat and dense matter that fills our newborn universe, setting the stage for the formation of galaxies, stars, and ultimately us. In this model, the Big Bang is not the absolute beginning, but a periodic event, a rebirth following a long phase of expansion and separation. One of the most significant strengths of the ekpyrotic model is its elegant solution to some of the biggest puzzles in cosmology, problems that the theory of inflation was specifically designed to solve. For instance, why is the universe so remarkably flat? And why does the cosmic microwave background radiation appear so uniform in all directions, a conundrum known as the horizon problem? Inflation solves these by proposing a period of ultra-rapid expansion that smoothed and flattened the early universe. The cyclic model, however, offers an alternative. Because the colliding branes are inherently flat and uniform, and because the collision occurs everywhere at once, the new universe is born already flat and homogeneous. The model essentially sets the initial conditions for a smooth universe from the very first moment, bypassing the need for a separate inflationary epoch. The gentle, slow pulling apart of the branes before the collision provides a natural explanation for the uniformity we observe, making the cycle itself the engine of cosmic order. This cyclical dance is governed by a delicate balance of forces. Dark energy, which we see as driving the accelerated expansion of our universe today, plays the crucial role of driving the branes apart after a collision. It ensures that each cycle has enough time for stars to form, planets to coalesce, and perhaps for life to arise. Then, over truly astronomical timescales, the attractive force between the branes overcomes dark energy's push, drawing them back together for another collision and another rebirth. This introduces a fascinating and testable prediction. If this model is correct, the accelerated expansion we see today is not a one-way ticket to a cold, empty death, but merely the prelude to the next cosmic rebirth. The fate of the universe is not heat-death, but an eternal, rhythmic dance of creation and destruction, where every ending is seamlessly woven into a new beginning. Long before modern string theory or conformal geometry, a simpler yet equally profound idea captured the imagination of scientists and philosophers: the oscillating universe theory. This concept strips the cosmic cycle down to its most fundamental elements, governed by the primal force of gravity. Imagine the universe not as a one-time explosion, but as a cosmic lung breathing in and out over eons. It begins with a big bang, expanding and cooling, allowing galaxies to form and life to emerge. But then, after billions of years, the expansion slows as gravity, the great attractor, begins to pull everything back together. Galaxies reverse their course, rushing toward one another. The sky grows hotter as background radiation is compressed, and eventually all matter and energy are drawn into a catastrophic collapse, a big crunch. In this view, the crunch is not a final end, but a reset button. The incredible density and heat become the very conditions for a new Big Bang, birthing a fresh universe from the ashes of the old in an eternal, rhythmic pulse. This idea has deep historical roots, resonating with ancient philosophical concepts of eternal return. But as a scientific model, it gained significant traction in the 20th century, particularly when the Big Bang theory was still competing with the steady-state model. For proponents of an oscillating universe, it offered an elegant answer to the troubling question of a beginning. If the universe has always been cycling, then the problem of a first cause simply vanishes. There is no need for a creation event, as the chain of universes extends infinitely into the past. Each cycle could last hundreds of billions of years, with the universe expanding to a maximum size before gravity finally wins out. The laws of physics might even reset with each new bang, offering an explanation for why our universe seems so finely tuned for life. If the constants of nature are reshuffled each cycle, it's statistically inevitable that one would eventually produce a habitable cosmos. However, this beautifully simple model faced a devastating challenge in the late 1990s. Astronomers, expecting to measure how much the universe's expansion was slowing down due to gravity, discovered the opposite: the expansion is accelerating. A mysterious repulsive force, which we now call dark energy, is pushing galaxies apart at an ever-increasing rate. This discovery fundamentally altered our cosmic forecast. Instead of a universe destined to eventually collapse under its own weight, we appear to live in one that will continue to expand forever, growing colder, darker, and more empty, a heat death. The observational evidence for accelerating expansion seemed to slam the door shut on the possibility of a big crunch, and with it, the classic oscillating universe theory. Gravity, it turned out, was not strong enough to reverse the cosmic expansion. Dark energy was the dominant force shaping our ultimate fate. Yet, the human imagination, especially in theoretical physics, is resilient. The core idea of a cyclical universe is so compelling that it has inspired modern revisions that attempt to reconcile it with the reality of dark energy. Some theorists propose that dark energy might not be constant. What if its strength changes over time? A model known as quintessence suggests that the energy driving the acceleration could eventually decay, weakening over trillions of years. If this happens, gravity could reassert its influence. After an unimaginably long period of expansion, the universe might finally stop, and begin the long journey back toward a crunch. In this scenario, the cycle isn't a rapid pulse but an incredibly drawn-out process, with each phase lasting far longer than the current age of our universe. Other revisions look to the quantum realm for a solution. The moment of the big crunch, like the Big Bang, is a singularity, a point where the laws of physics as we know them break down. But many physicists believe that a theory of quantum gravity, which unites general relativity with quantum mechanics, would eliminate this singularity. Instead of collapsing to an infinitely dense point, the universe might reach a maximum density and then bounce due to repulsive quantum forces. This concept, known as the quantum big bounce, transforms the oscillating universe model. The cycle is no longer a matter of classical gravity reversing the expansion, but a quantum transition from a contracting phase to an expanding one. In this modern interpretation, dark energy doesn't necessarily prevent the cycle. It might simply be a feature of the expansive phase we currently inhabit, with its role changing as the universe evolves through its immensely long life cycle. The dream of an eternal, oscillating cosmos, while challenged, has evolved, finding new life at the frontiers of quantum physics. But what if the very fabric of reality, the stage upon which this cosmic drama unfolds, is not a smooth, continuous sheet as Einstein envisioned? To explore a truly fundamental cycle, we must venture down to the smallest conceivable scales, to a theory that suggests spacetime itself is pixelated. This is causal-set-theory, a compelling approach to quantum gravity that proposes a universe built not from a seamless continuum, but from discrete, indivisible building blocks, the atoms of space and time. In this view, the smooth geometry of general relativity is an illusion, a large-scale average of a fundamentally granular reality. Much like a digital photograph appears smooth from a distance but reveals its pixelated nature when you zoom in. This radical rethinking of spacetime's nature opens up a profoundly different pathway to a cyclical cosmos, one that operates not through grand collisions or gravitational collapse, but through the step-by-step growth of the universe's most basic structure. The central idea of causal-set theory is elegantly simple. The theory posits that the history of the universe can be represented by a causal set, a vast collection of these elementary spacetime points connected to one another by a relationship of cause and effect. Each point or atom has a before and an after. If one event can influence another, a link exists between their corresponding points. The entire four-dimensional history of the cosmos, with all its events from the Big Bang to this very moment, is encoded in this vast, shimmering web of causal connections. What we perceive as the smooth, flowing river of time is actually the unfolding sequence of these discrete moments being added to the set. Time, in this picture, is not a background parameter but a direct consequence of this sequential growth process. The universe, quite literally, builds itself one moment at a time. This discrete framework offers a powerful escape from the problem of singularities that plague classical cosmology. In general relativity, the Big Bang is a point of infinite density where the equations break down. But in causal-set theory, there is no such thing as an infinitely small point. There is a fundamental limit to how small a volume of spacetime can be, dictated by the Planck scale. Therefore, the universe could not have emerged from a true singularity. Instead, we can imagine a process where the causal set grows from a much simpler initial state. Perhaps it began with just a single element, a lone atom of spacetime. Then another element was born from it, connected by a causal link. This process continued, with new elements being added, each new moment crystallizing out of the quantum possibilities of the previous ones, gradually building up the complex, four-dimensional universe we inhabit today. It is within this process of sequential growth that the potential for cyclicity emerges. The growth of the causal set is governed by probabilistic quantum rules. While it seems to be expanding and becoming more complex in our current epoch, the theory does not necessarily dictate that this must continue forever. Some formulations suggest that the growth could eventually slow, stop, or even reverse. Imagine the causal set reaching a state of maximum size and complexity. At this point, the process could transition. Instead of adding new elements, the universe might begin a phase of sequential dissolution, where elements are removed from the set. This would not be a dramatic collapse like a big crunch, but a quiet fading away of reality at the most fundamental level, a kind of cosmic forgetting, where moments of spacetime simply cease to exist, breaking causal links and simplifying the web. This dissolution phase could continue until the universe is reduced back to a simple, elementary state, from which a new cycle of growth could begin anew. In this model, the cosmic cycle is not a violent rebound but a gentle, quantum mechanical process of breathing in and breathing out at the Planck scale. This perspective completely reframes our understanding of a universe's beginning and end. There is no fiery bang or icy crunch, only the initiation and completion of a growth process. The Big Bang, in this view, would simply mark the start of a particularly rapid phase of growth in our local region of the causal set. The heat death of the universe could correspond to the causal set reaching a state of maximum size and equilibrium, where growth becomes incredibly slow or ceases altogether, setting the stage for the eventual dissolution phase. Causal-set theory thus provides a starkly minimalist yet profoundly deep mechanism for an eternal cycle, one where the universe perpetually reconfigures its own fundamental building blocks, forever weaving and unweaving the tapestry of spacetime itself. Now, if the idea of spacetime being built from discrete atoms is mind-bending, prepare for a concept that challenges the very nature of dimensionality itself. This is the holographic principle, a revolutionary idea born from the study of black holes that suggests our vivid, three-dimensional reality. Everything we see, touch, and experience might be a grand illusion, a projection of information stored on a distant, two-dimensional surface. It's a theory that not only redefines what the universe is, but also opens up a breathtaking possibility for cosmic rebirth, a form of recycling more fundamental than any we've yet considered. To grasp this, we need to start with black holes, the cosmic paradoxes that gave rise to this idea. In the 1970s, physicist Jacob Bekenstein made a startling proposal. A black hole, an object so dense that not even light can escape, must have entropy. Entropy is a measure of disorder, or, more precisely, of the number of ways a system's internal components can be arranged without changing its overall appearance. A high-entropy system is one with a lot of hidden information. Bekenstein realized that a black hole's entropy is not contained within its volume, as you might expect, but is instead proportional to the surface area of its event horizon, the point of no return. This was counterintuitive. Usually, the entropy of an object grows with its volume, but for a black hole, the information content seemed to be painted onto its boundary. Stephen Hawking later built on this, showing that black holes aren't completely black. They emit a faint radiation and slowly evaporate over astronomical timescales. This raised a terrifying question for physicists. What happens to all the information about the stars, gas, and anything else that fell into the black hole? If the black hole evaporates completely, does that information vanish from the universe forever? This would violate a cornerstone principle of quantum mechanics. That information can never be truly destroyed. The potential solution proposed by Gerard T. Hooft and Leonard Susskind was the holographic principle. They suggested that the information isn't lost because it was never actually inside the black hole to begin with. Instead, it is perfectly encoded like a cosmic pixel map on the event horizon's two-dimensional surface. The three-dimensional interior we imagine is a projection of that data, much like a hologram, a three-dimensional image created from a two-dimensional film. The truly radical leap is applying this principle not just to black holes, but to the entire universe. If a region of space with a boundary can be described by a theory on its boundary, then perhaps our entire observable cosmos is a vast hologram. The three-dimensional space we inhabit, with its galaxies, planets, and people, could be a projection from a two-dimensional surface at the very edge of what we can see. In this view, the universe is like a movie screen, and we are the characters in the film, unaware that our reality is being generated from the data encoded on the flat screen surrounding us. This isn't just a philosophical curiosity. It has concrete mathematical underpinnings in string theory, where certain physical processes in a volume of space can be perfectly described by a theory that exists on its boundary, a concept known as the ad-s/safety correspondence. So how does this lead to a cyclical universe? The connection lies in the ultimate fate of information. In our current cosmic forecast, the universe ends in heat death, a cold, dark, empty expanse. But according to the holographic principle, the information that defines our universe never disappears. It remains encoded on the cosmological horizon, the ultimate boundary of our observable cosmos. Now imagine this final state. The universe is vast, cold, and virtually empty, but its two-dimensional boundary is packed with the maximum possible amount of information, a complete blueprint of everything that ever was. This dormant data shell could, in principle, become the seed for a new cycle. The transition might work like this. The holographic universe has a maximum information capacity, just like a hard drive. This limit is defined by the area of its boundary. As our universe approaches heat death, it reaches this maximum entropy state. The cosmic hard drive is full. But what if a quantum fluctuation, a random flicker in the underlying fabric of reality, triggered a process that reset the system? The information on the boundary could be reprocessed, acting as the initial conditions for a new Big Bang. The two-dimensional data is translated back into a new, hot, dense, three-dimensional universe. In this model, cosmic rebirth isn't about matter collapsing and bouncing. It's about information being read out again. Each new cycle would inherit the memory of the previous universe in its fundamental parameters, but the specific history, the arrangement of galaxies, the rise and fall of civilizations might be scrambled or reset. The holographic principle thus offers a form of cosmic recycling that is both elegant and profoundly strange, suggesting that the universe is not just in a loop of space and time, but in a loop of information itself, forever writing and rewriting its own story on the boundary of reality. If the holographic principle suggests our reality is a projection, then loop quantum cosmology proposes that the very fabric of space has a tangible, woven structure. This theory takes us from the ethereal realm of information directly into the physical mechanics of a cosmic rebound, offering perhaps the most rigorously defined model of a cyclical universe to date. Born from the ambitious quest to merge general relativity with quantum mechanics, loop quantum gravity, or LQG, reimagines space itself. Instead of a smooth, continuous backdrop, space is visualized as a network of finite, woven loops, an intricate fabric of interconnected threads at the smallest possible scale, the Planck length. These loops are the fundamental quanta of space. You cannot have half a loop, just as you cannot have half an electron. This granular nature of space has a stunning consequence when applied to the entire cosmos. It completely eliminates the Big Bang singularity. In the standard model, as we rewind time, the universe gets hotter, denser, and smaller, all the way down to an infinitely dense point where our equations fail. But in loop quantum cosmology, this simply cannot happen. Think of space as a stretched elastic band. You can stretch it quite far, but if you try to compress it past a certain point, it resists with a powerful, inherent springiness. Similarly, as the universe collapses under its own gravity towards what would be a big crunch, it reaches a maximum possible density dictated by the tiny quantum loops. At this critical threshold, a powerful repulsive force generated by the quantum geometry itself kicks in. This isn't a force like gravity or electromagnetism. It is a fundamental property of space resisting its own destruction. Instead of collapsing into a singularity, the universe hits a cosmic trampoline. the collapse halts and reverses, leading to a rapid, explosive expansion, a big bounce. The Big Bang, in this view, was not the absolute beginning, but a transitional phase, a moment of cosmic renewal. This leads to a profound redefinition of what came before our universe. The pre-Bang universe wasn't an empty void or a different dimension. It was a full-fledged contracting cosmos, likely similar in many ways to our own. It would have had its own galaxies, stars, and perhaps even life, all collapsing inward under gravity. As it contracted, the temperature would have risen and the cosmic background radiation would have blue-shifted to higher and higher energies. But just before reaching the point of infinite density, the quantum repulsion took over, and all that collapsing matter and energy were reborn into the expanding universe we inhabit. The immense heat and density of the Big Bang were simply the natural inheritance from the contracting phase, heated to an unimaginable degree by the compression itself. One of the most compelling aspects of this model is its ability to explain the origin of the large-scale structure we see today. In the standard inflationary Big Bang model, the seeds for galaxies are planted by random quantum fluctuations during a brief period of hyperfast expansion. Loop quantum cosmology offers an elegant alternative. The universe that collapsed before ours would have had its own complex structures. During the contraction phase, those structures were stretched and squeezed, but the quantum fluctuations associated with them, tiny ripples in density, would not have been erased. As the universe passed through the bounce, these fluctuations would have been imprinted onto the hot, dense plasma of the newborn universe. The gravitational fingerprints of a previous cosmic cycle could thus serve as the primordial seeds. When our universe began expanding, these inherited imperfections were amplified by gravity, eventually growing into the vast cosmic web of galaxies and clusters we observe today. In a very real sense, the ghost of a former universe may be etched across our night sky. Yet, for all the intricate mechanics proposed by theories like loop quantum gravity, there is an even broader canvas upon which the possibility of cosmic cycles might be painted. This brings us to a hypothesis that radically recontextualizes our place in the grand scheme of things, the multiverse selection hypothesis. To understand this, we must first embrace the staggering idea that our entire universe, with its hundreds of billions of galaxies, might be nothing more than a single bubble in a boundless, eternally frothing cosmic ocean, a multiverse. The leading mechanism for this is eternal inflation, a theory suggesting that the rapid expansion of space we call inflation didn't just happen once in our universe. Instead, it may be a perpetual, fundamental feature of a much larger meta-reality. In this endless expanse, the vacuum of space possesses a strange, high-energy state that drives exponential expansion. But this vacuum is unstable, and in random locations it can decay like a bubble forming in a pot of boiling water. Each of these decay events releases a colossal amount of energy, sparking a hot Big Bang and birthing a new, self-contained universe within the ever-inflating background. Our cosmos is just one such bubble among an infinite number. Within this infinite ensemble, the specific laws of physics are not universal commandments. They are more like local bylaws set randomly during the bubble nucleation process. The strength of gravity, the mass of an electron, the number of spatial dimensions, these fundamental constants could be different in every single bubble universe. The vast majority of these universes would be stillborn, perhaps with forces too weak to form atoms or too strong for nuclei to ever stabilize. They would be barren, simple, and devoid of any complexity. But in an infinite multiverse, every possible combination of physical constants, no matter how improbable, will be realized somewhere. Our universe, with its seemingly perfect fine-tuning for complexity and life, isn't a miraculous anomaly, it's simply a statistical inevitability. This is the essence of the anthropic principle. We find ourselves in a universe capable of supporting our existence because we couldn't possibly observe one that doesn't. Now, where do time loops fit into this sprawling picture? The multiverse selection hypothesis proposes that a cyclical nature might be one of those rare, finely tuned properties. Consider what it takes for a universe to be cyclical. It needs a very specific set of physical laws, a precise balance between the forces of expansion and contraction, or a quantum geometry that permits a bounce. A universe that simply expands forever into heat death cannot loop. A universe that collapses too quickly into a big crunch might not allow time for stars and planets to form, preventing the rise of observers who could even contemplate the cycle. Therefore, a universe that is both habitable and cyclical might be an exceptionally rare combination. But across an infinite multiverse, even the rarest of possibilities must occur. In fact, one could argue that a cyclical universe has a distinct selective advantage over a linear one in the grand evolutionary landscape of the multiverse. A linear universe has one chance, one finite timeline to produce complexity before fading into eternal darkness. A cyclical universe, however, gets endless opportunities. With each new cycle, it can try again, potentially allowing for processes that accumulate complexity or stability over vast cosmic timescales. This idea connects deeply to the concept of eternal inflation itself. The inflating background is, in a sense, eternal to the future. New bubbles are constantly being born, but what about its past? Could it be eternal as well? Some models suggest that the inflating state might not have a beginning, that it has always been creating new universes. If that is true, then the entire multiverse system is itself a form of a time loop on the grandest conceivable scale, an eternal process of creation that never had a starting gun. Our own universe's potential cycle, whether a bounce, a holographic reset, or a brain-world collision, would then be a small, nested loop within this infinitely larger, self-sustaining metacycle. We are not just in a time loop, we are in a time loop within a time loop, a fractal pattern of birth and rebirth echoing across multiple levels of reality. The multiverse selection hypothesis doesn't just allow for our cosmic cycle. In a profound way, it might make our existence within such a cycle almost inevitable, a natural consequence of a meta-reality where every possible story gets told, and the most enduring stories get to be told again and again. This idea of an infinite multiverse acting as a breeding ground for cyclical universes finds one of its most powerful expressions in the theory of eternal inflation. To grasp this, we need to revisit the very earliest moments of our own universe, a fraction of a second after the Big Bang. The prevailing theory of cosmic inflation proposes that space itself underwent a period of incredibly rapid, exponential expansion, smoothing out the cosmos and planting the seeds for future galaxies. But what if that inflationary period didn't just stop? What if, for most of the meta-reality we're embedded in, it never stopped at all? This is the core of eternal inflation. Imagine a vast, boiling ocean. The water itself represents a high-energy, unstable state of space called the inflaton field. This field is constantly trying to decay to a lower, more stable energy level. But here's the catch. The expansion of space in this high-energy state is so fiercely rapid that it outpaces the decay. The overall ocean is growing at an unimaginable rate, and within this churning expanse, pockets of stability occasionally form. These are like bubbles rising in the boiling water. Each bubble is a region where the inflaton field has finally decayed, releasing its pent-up energy in a tremendous flash. That flash contained within the bubble is a Big Bang. Our entire observable universe is just one such bubble, one island of stability in an endless, ever-expanding sea of primordial inflation. Within this framework, the possibilities for cosmic cycles become truly limitless. Each bubble universe nucleates with its own random set of physical laws and constants. Some might expand for a brief moment before collapsing. Others might fly apart forever into darkness, but a select few, governed by the precise physics we've been exploring, like a quantum bounce or a brain-world collision, would be cyclical. They would have their own internal, closed time-like curves, their own rhythms of birth, death, and rebirth. In this grand picture, our universe's potential cycle is not a singular, special event. It is merely one local pattern of recurrence within an infinite ensemble. While our bubble might go through its own sequence of bangs and crunches or expansions and resets, the larger inflating background continues its relentless expansion, providing an eternal stage upon which an infinite number of other cosmic dramas are simultaneously unfolding. The end of our cycle would not be the end of everything. It would be a local event unnoticed in the grand meta-realm where new bubbles are constantly being born. This leads to a fascinating implication for the very nature of time in such a multiverse. If the inflating background is truly eternal, with no beginning or end, then the concept of a first cycle becomes almost meaningless. There could be bubble universes that are infinitely older than our own, having gone through an endless number of cycles before our bubble even nucleated. Time as we experience it within our bubble is linear and sequential, but from the perspective of the multiverse, time is a vast, tangled web of these separate timelines, each with its own rhythm and its own history. Some cycles might be short and violent, others could be long and slow, allowing for complex structures to arise again and again. The multiverse doesn't just allow for cycles, it makes them a statistical certainty, ensuring that every possible type of universe, including those that are eternally recurring, will come into existence an infinite number of times. From the grand architecture of the multiverse, we now turn to a model that finds the potential for rebirth not in cosmic collisions or quantum geometry, but in the quietest and most profound stillness imaginable. This is the Phoenix Universe model, a concept that embraces the bleakest forecast for our cosmos' eternal heat-death, and discovers within that final emptiness a spark for new creation, a cosmic resurrection more miraculous than any bounce or collision. The name itself is deeply evocative, drawn from the mythical bird that cyclically regenerates, rising from its own ashes. In this scientific incarnation, the ashes are the cold, dark, and utterly random state of maximum entropy that marks the end of our universe's story. To understand how life could possibly spring from this cosmic grave, we need to fully appreciate the nature of heat-death. After trillions upon trillions of years, all energy gradients will have evened out. The universe will be a vast, lukewarm bath of fundamental particles and radiation, spread with near-perfect uniformity across an unimaginable void. There will be no stars to give light, no planets to orbit them, and no processes of any kind, because all work requires a difference in energy, a hot spot and a cold spot. In this state of equilibrium, time, as we understand it, effectively loses its meaning. Nothing happens, and nothing will ever happen again. It is the ultimate end of activity, a final and permanent silence. The Phoenix model does not seek to avoid this fate, it accepts it as a necessary stage. The universe must first die before it can be reborn. The mechanism for this rebirth lies in the bizarre rules of the quantum world, which remain active even in this final, frozen state. In complete emptiness, at the absolute zero of activity, quantum mechanics tells us that the void is not truly empty. It is a seething foam of virtual particles, constantly flickering in and out of existence due to the Heisenberg uncertainty principle. These are tiny, spontaneous fluctuations in energy. Over an ordinary timescale, these fluctuations are insignificant, far too small to upset the cosmic equilibrium. But the Phoenix model asks us to consider timescales that dwarf even the age of our universe. We are talking about time spans so vast they are expressed with double exponents, numbers like 10 to the power of 10 to the power of 100 years. Over these truly eternal durations, even events of astonishing improbability become not just possible but inevitable. One pathway for rebirth is through a process called quantum tunneling. Imagine the state of the universe as a ball resting in the bottom of a valley. The valley represents heat death, a stable, low-energy state. To get to a new Big Bang, a new high-energy state, the ball would need to be kicked up and over a tremendous energy barrier, which is impossible in a dead universe with no source of energy. Quantum tunneling provides a ghostly alternative. There is a tiny but non-zero probability that the ball could simply disappear from its valley and reappear on the other side of the mountain without ever having to climb it. It doesn't traverse the space in between, it effectively cheats its way through. In cosmic terms, a random quantum fluctuation in the uniform vacuum could, by sheer unimaginable luck, tunnel into a patch of space with the exact conditions of a nascent universe. This patch would then inflate in a tiny, localized Big Bang, birthing a new cosmic domain within the dead expanse of the old one. Another, even more mind-bending possibility relies on a mathematical concept known as Poincaré recurrence. This theorem, applied to a system with a finite number of possible states, states that given enough time, the system will eventually return to a state arbitrarily close to its initial configuration. If our universe, even in its heat-dead form, has a finite number of quantum states, then over an infinite amount of time, it must eventually fluctuate back into a state identical to the hot, dense, low-entropy condition of the Big Bang. It wouldn't be a bounce or a reversal of collapse, it would be a random, statistical resurrection. The universe would simply reorganize itself by chance into a new beginning. The overwhelming improbability of this event is balanced by the infinite time available, making it a mathematical certainty. In this view, the cycle is not a rhythmic pulse but a sporadic, rare event, a cosmic jackpot that gets hit every once in a near eternity. The profound implication of the Phoenix model is that it requires no special laws of physics. It doesn't need extra dimensions, holographic boundaries, or loop quantum gravity. It operates entirely within the known rules of thermodynamics and quantum mechanics, pushing them to their ultimate logical conclusion. It suggests that even in a universe destined for the coldest, most final death imaginable, the seeds of new life are always present, waiting in the quantum static for their moment to bloom across an infinity of time. Our universe may not be in a tight, regular loop, but part of a vast, sporadic cycle of death and resurrection, where each new genesis is a lonely island of order in an endless sea of silence, each one completely unaware of the ghosts of universes that came before. But to explore a universe where time itself might fold back on itself, we first need to understand why time feels like a one-way street in the first place. This brings us to one of the most fundamental puzzles in all of physics, the arrow of time. Why do we remember the past but not the future? Why does a shattered glass not spontaneously reassemble itself? The answer, according to the second law of thermodynamics, is entropy. Entropy is a measure of disorder, and the second law states that in any closed system, the total entropy can only increase or stay the same over time. It's the reason heat flows from a hot cup of coffee to the cool room, never the other way around. This relentless drive toward greater disorder gives our universe its perceived direction, its arrow. The past is a state of lower entropy, and the future is a state of higher entropy. We are all riding this wave of increasing disorder from the highly ordered, low-entropy state of the Big Bang toward the ultimate high-entropy state of heat death. Now, imagine a cyclical universe that is truly time-symmetric. This is a cosmos where the arrow of time doesn't just point forward forever. Instead, at the universe's moment of maximum expansion, the turning point between expansion and contraction, the arrow of time might reverse. In this fascinating model, the second law of thermodynamics would still hold, but its apparent direction would flip. From the Big Bang up to the point of maximum size, entropy increases just as we observe. But as the universe begins to contract under gravity, heading toward a big crunch, entropy would effectively start to decrease. From our perspective, living on the expanding side of the cycle, this is nearly impossible to visualize. It would mean that during the contraction phase, broken glasses would spontaneously reassemble, heat would flow from cold objects to hot ones, and people would live their lives backward from death to birth, with their memories forming of the future and fading for the past. The appeal of such a model is its profound elegance. It resolves the mystery of why the Big Bang had such an incredibly low entropy to begin with, a special, finely tuned initial condition that physicists have long grappled with. In a time-symmetric cycle, the Big Bang's low entropy isn't a mysterious starting point. It's a natural consequence of being the temporal mirror image of the Big Crunch. The crunch is a state of extremely high entropy, a chaotic mess of particles and radiation. If time reverses at that moment, then the crunch becomes the bang for the next cycle. But from the reversed time perspective, that high entropy crunch is seen as a low entropy beginning. The universe would be like a bouncing ball, with time flowing forward on the way up and backward on the way down, creating a perfect, seamless loop with no need for a special initial condition. However, this beautiful idea faces monumental challenges, the greatest of which is the existence of complex structures like galaxies, stars, and conscious life. The problem is one of consistency. For the cycle to be truly smooth and symmetric, the universe would have to retrace its steps with near-perfect precision during the contraction phase. But could it? The formation of a galaxy is an incredibly complex, chaotic process involving gravitational collapse, supernova explosions, and the merging of smaller structures. These processes generate immense amounts of entropy. For the universe to run them in reverse during the contraction, all those scattered particles and dissipated energy would need to find their way back into stars and galaxies, meticulously reassembling everything that existed. It seems astronomically unlikely that the random motions of countless particles during a gravitational collapse would perfectly mirror their paths from the expansion era. The universe would likely just become a hotter, denser, and even more chaotic mess as it crunched, not a beautifully rewinding film of its own history. This leads to a critical fork in the road for cyclical theories. Some physicists argue that a true time reversal is impossible for a universe containing complex observers. The very processes of star formation and biological life are irreversible engines of entropy production. We are testament to the arrow of time. Therefore, a more plausible cyclical model might be one where the arrow of time does not reverse. In this scenario, entropy continues to increase even during the contraction phase. The universe would then approach the Big Crunch not as an orderly reversal, but as a state of maximum chaos. This presents a different problem. How do you get a new, low-entropy Big Bang from a high-entropy crunch? This is where the quantum bounce models we discussed earlier, like loop quantum cosmology, become so important. They provide a mechanism, a quantum repulsion, that bypasses the singularity and resets the entropy clock, not by reversing time, but by triggering a new expanding phase from the ashes of the old. In this view, the cycle is not a symmetrical pendulum swing, but more like a heartbeat, with each new beat starting fresh, carrying forward the material but not the specific history of the previous cycle. The arrow of time plunges forward relentlessly, even across the bounce, leaving the symmetrical dream of a rewinding cosmos as a tantalizing but potentially unattainable ideal. While the theories of bounces and branes offer mechanical models for a cycle, another perspective comes from a radical rethinking of reality itself, one that suggests the entire cosmos operates like a cosmic hologram in a far deeper way than we've yet considered. This is the world of physicist David Bohm and his concepts of the implicate order and the hollow movement. Bohm was deeply troubled by the fragmented nature of standard quantum theory and sought a description of reality that was fundamentally whole and undivided. He proposed that the world we perceive with its separate objects, clear boundaries, and flowing time is just a surface level of a much deeper, hidden reality. He called our everyday world the explicate order, which is literally the unfolded or unfolded aspect of the cosmos. But beneath it lies the implicate order, a realm where everything is enfolded into everything else, a state of total unity where past, present, and future exist simultaneously in a timeless, seamless whole. To grasp this, think of the process of a hologram. A standard holographic film looks like a meaningless pattern of swirls, yet when illuminated with a laser, a full three-dimensional image unfolds from it. Every single part of that film contains information about the entire image. If you were to cut the film into tiny pieces, each fragment would still project the entire scene, albeit with less clarity. For Bohm, the universe operates in a similar way. At the fundamental level, the entire cosmos is enfolded into every single region of space. An electron here and a galaxy far, far away are not truly separate. Their seeming isolation is an illusion emerging from the unfolding of a deeper, interconnected reality. He called the dynamic process of constant unfolding and enfolding the holomovement, the flowing, vibrant activity that gives rise to our experienced world. Applying this to cosmology opens a breathtaking vista for understanding a cyclical universe. The Big Bang, in Bohm's view, would not be the creation of the universe from nothing, but a moment of supreme unfolding. It is the point at which the implicate order, the timeless, enfolded totality of cosmic history, begins to express itself as the explicate order of space, time, and matter. The entire history of the universe, from its first moments to its final state, was already enfolded or implicit in that initial state. The subsequent 14 billion years of expansion and evolution are simply the gradual revelation, the unfolding of that which was always there. The cosmos is not so much evolving toward something new as it is manifesting what is already latent within it. This leads directly to a cyclical interpretation. If the beginning is a great unfolding, then the end of the cosmic cycle must be a corresponding great enfolding. As the universe reaches its final state, whether a heat death or a big crunch, the process reverses. The explicate order, with all its separated galaxies, stars, and histories, begins to fold back into the implicate order. All the events, all the information, all the structures that ever existed become re-enfolded into the unified whole. The end of the universe is not an annihilation, but a return to the source. From this perspective, the cycle is not a series of disconnected reboots, but a single, continuous process of breathing. An outward breath of unfolding, the bang and expansion, followed by an inward breath of enfolding, the crunch or dissolution, all happening within a timeless, eternal reality. Each cycle is a complete expression of the implicate order, a single cosmic thought being thought and then reabsorbed. Bohm's ideas find a surprising resonance with the strange phenomenon of quantum non-locality, which he called the quantum potential. This is the aspect of quantum theory that allows two entangled particles to instantaneously influence each other regardless of the distance separating them, a connection that seems to defy the speed of light limit. For Bohm, this wasn't a spooky anomaly, it was direct evidence for the implicate order. The entangled particles are not communicating faster than light because at the fundamental level they are not truly separate. Their apparent separation is part of the explicate illusion. In the implicate order, they remain a single, undivided whole. This non-local connectedness could be the hidden mechanism that ensures the coherence of the cosmic cycle. The information needed to orchestrate the grand enfolding at the end of a universe and the subsequent unfolding of the next is not transmitted through space and time. It is present everywhere at once, woven into the fabric of the implicate order itself, guiding the holomovement with a kind of cosmic intelligence that ensures the integrity of the eternal return. But what if the cosmic cycle is even more intimate than a grand bounce or a holographic reset? What if the seeds of new universes are being sown all around us, hidden within the most enigmatic objects in the cosmos? This brings us to one of the most provocative and mind-bending theories of all, black hole cosmology. It's an idea that suggests our entire universe, with all its hundreds of billions of galaxies, might not be the top-level reality. Instead, we could be living inside a black hole that formed in a much larger parent universe. And in a stunning twist of cosmic recursion, every black hole that forms within our own cosmos could itself contain an entirely new universe, leading to a fractal, tree-like structure of reality where creation is happening on an infinite number of scales. To understand this, we need to reframe our perspective on the Big Bang. The standard model describes it as an explosion that happened everywhere at once, but from a mathematical standpoint, it shares a striking resemblance to the interior of a black hole. Imagine you are an astronaut falling into a stellar mass black hole. As you cross the event horizon, the point of no return, you might not notice anything immediately different. But as you continue inward, the gravitational forces become immense, stretching you and compressing you in a process physicists call spaghettification. All paths lead to the center, to the singularity, a point of infinite density where the known laws of physics break down. Now, rewind the film of our universe's expansion. Galaxies are rushing together, the universe is getting hotter and denser, and all paths lead back to the initial singularity of the Big Bang. The mathematical description of a collapsing universe heading toward a big crunch is eerily similar to the description of matter falling into a black hole singularity. Black hole cosmology proposes that this is not a coincidence. The Big Bang was a singularity, but it was the singularity at the heart of a black hole in a pre-existing universe. This idea flips the script on creation. In this model, our universe was born when a massive star in a parent universe collapsed, or when two such parent universe black holes merged. The incredible energy and density of that collapse were so extreme that they triggered the formation of a new space-time continuum, with its own dimensions and physical laws, which began expanding inside the black hole. From the perspective of the parent universe, the formation of our cosmos was just another black hole coming into existence. But from our perspective inside, it was the beginning of everything. The event horizon of that parent universe black hole would then correspond to a cosmological horizon for us, a boundary we can never see beyond because it lies in our own ultimate past. This leads to the theory's most profound implication, a fractal multiverse. If our universe was born from a black hole in a larger cosmos, then it stands to reason that the black holes within our own universe are themselves cosmic wombs. When a massive star in our universe goes supernova and collapses into a black hole, the singularity at its center could be the Big Bang for a brand new universe. This new universe would be entirely separate from our own, with its own space-time, possibly even with different fundamental constants and numbers of spatial dimensions. It would be forever causally disconnected from us. Nothing that happens in that baby universe can affect ours, and vice versa. We would simply observe the black hole from the outside as a gravitational trap from which nothing escapes. But on the inside, an entire cosmic history could be unfolding, complete with its own galaxies, stars, planets, and perhaps even life, completely unaware that their entire reality is contained within an object we perceive as a dark, silent void. This creates a breathtaking vision of reality as a cosmic Russian nesting doll or an infinite branching tree. Each universe gives birth to countless others through the formation of black holes, and each of those child universes does the same. There is no top and no bottom to this hierarchy. It's turtles, or rather universes, all the way down and all the way up. This provides a natural mechanism for a cyclical cosmos, but not in the traditional sense of one universe rebooting into itself. Instead, it's a cycle of prolific reproduction, where universes give birth to new universes in a process that could be eternal. A major question this theory attempts to address is the fate of information. The black hole information paradox asks what happens to all the information about the matter that falls into a black hole if the black hole eventually evaporates via Hawking radiation. Black hole cosmology offers a radical solution. The information isn't lost, it is translated. When matter and energy cross the event horizon and plunge toward the singularity, that information isn't destroyed. Instead, it gets reprocessed and becomes part of the initial conditions for the new universe being born inside. The specific properties of the infalling material, the number of particles, their energies, their quantum states, could influence the fundamental constants and the initial density fluctuations of the baby universe. In this way, a form of cosmic heredity could exist. A universe born from the collapse of a star rich in carbon might have physical laws that favor carbon-based chemistry, while a universe born from the collision of two black holes might have a different set of rules altogether. This introduces a mind-boggling possibility. The fine-tuning of our universe for life might not be a random accident, but an inheritance from the specific conditions of the black hole that gave us birth. This concept of a fractal multiverse, where universes nest within black holes, presents a physical mechanism for cosmic cycles. But what if the cycles are not a feature of physical reality at all, but of the very code that defines it? This brings us to a theory that has leapt from science fiction into serious scientific debate, the simulation hypothesis. The idea is that our universe, with all its vastness and complexity, might not be base reality, but an advanced digital construct, a simulation running on a computer of unimaginable power. When we view this hypothesis through the lens of a cyclical cosmos, a fascinating possibility emerges. The first time loop might not be a physical event, but simply the initial boot-up sequence or a programmed reset function in the cosmic code. Think of it like this: when you start up a sophisticated video game, the virtual world doesn't pop into existence instantly. There's a loading screen, an initialization process where the fundamental rules of the game world are established. The laws of physics, the constants of nature, the initial conditions. What we perceive as the Big Bang could be exactly that, the moment the simulation was rendered operational. The incredible density and energy of that first moment would correspond to the massive computational power required to initialize an entire universe. And just as a game can be saved, closed, and then reloaded from a save state, our universe might be part of a cycle where the simulation is run, allowed to develop, and then reset back to its initial parameters to run again. This reset wouldn't be a gravitational collapse or a quantum bounce, but a simple command from the operators, a Control-Alt-Delete on a cosmic scale. The loop is not a law of physics within the simulation, but a feature of the hardware and software running it from the outside. If this is true, what might we look for as evidence? Proponents of the simulation hypothesis often point to potential glitches in the matrix, strange, seemingly irrational behaviors in the laws of physics that could be interpreted as programming errors or computational shortcuts. For instance, the bizarre rules of quantum mechanics, where particles exist in multiple states until observed, could be seen as a way to save processing power, only rendering the fine details of reality when something is looking at them. In a cyclical simulation, we might also look for signs of conservation. Just as a computer program has conservation laws for memory and processing cycles, our universe has its own strict conservation laws for energy, momentum, and charge. These could be fundamental rules hard-coded into the simulation to ensure it runs efficiently and stably across countless cycles. The most compelling potential evidence, however, is the infamous fine-tuning of the universe. The fundamental constants of nature, the strength of gravity, the mass of an electron, the cosmological constant, seem perfectly calibrated to allow for the existence of galaxies, stars, planets, and life. If even one of these numbers were slightly different, the universe would be barren. From a simulation perspective, this isn't a miraculous accident. It could be intentional design. The programmers may have tuned these parameters specifically to create a universe complex enough to be interesting, perhaps to study the evolution of consciousness or the emergence of complex systems, running the simulation over and over to observe different outcomes. This leads to the profound and unsettling question of purpose. Why would an advanced civilization run a universe simulation on a loop? The motivations could range from the scientific to the existential. Perhaps we are part of a grand experiment, a cosmic petri dish where the creators are testing theories of cosmology or sociology. Each cycle could be a separate trial with slightly varied initial conditions, and we are merely one iteration in a vast data set. Alternatively, the simulation might serve as a historical archive or a form of entertainment, a way for a post-biological civilization to experience the thrill of a cosmic drama again and again. A more philosophical possibility is that the simulation is a form of ancestor simulation, created by a far future civilization to understand its own origins. In this scenario, the creators might themselves be simulations within a simulation, leading to an infinite regress of nested realities, each one cyclical in nature. The very concept of a first loop becomes meaningless, as every universe is just a subroutine in an endless chain of cosmic computation. Whether we are experimental subjects, entertainment, or digital ancestors, the simulation hypothesis offers a chillingly elegant explanation for a cyclical cosmos, one where the laws of physics are simply the user manual for a reality we did not create. But to truly understand what might have happened before our universe began its expansion, we must confront the moment where our best theories of the large and the small simply fail. This is the realm of the Planck epoch, the first 10 to the minus 43 seconds of cosmic history, a duration so brief it defies human imagination. Within this infinitesimal sliver of time, the universe was compressed into a volume smaller than a single atom, yet containing all the energy and matter we see today. At such extreme densities and temperatures, the smooth, geometric picture of spacetime painted by Einstein's general relativity shatters. Gravity, described as the curvature of spacetime, becomes a wildly fluctuating quantum force. To peer into this primordial moment, we need a theory that can marry the rules of the quantum world with the description of gravity, a complete theory of quantum gravity. While we do not yet have a final answer, exploring the leading candidates opens a window to a reality that could have existed before the Big Bang, suggesting our universe's birth was not a beginning but a transition. One of the most promising frameworks for this is string theory. In this view, the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy strings. Different vibrations of these strings correspond to different particles, like electrons or photons, and crucially, one particular vibration pattern is believed to correspond to the graviton, the hypothetical quantum carrier of the gravitational force. This elegantly incorporates gravity into the quantum world. When we apply string theory to the very beginning, the concept of a singularity, a point of infinite density, often disappears. The theory suggests that as we rewind time, the universe does not collapse to a true infinity. Instead, it may have existed in a different state altogether. Some string-theoretic models propose a pre-Big Bang phase, where the universe was actually contracting, but in a specific way related to the properties of the strings and extra dimensions. In this scenario, the Big Bang was not an explosion from nothing, but a bounce from a contracting phase to our current expanding one, a cosmic turning point driven by the unique dynamics of fundamental strings. A different but equally profound approach comes from loop quantum gravity, which we touched on earlier. As a reminder, LQG proposes that space itself is not continuous, but is woven from a fabric of finite, interconnected loops. This granular structure has a direct and dramatic consequence for the Big Bang. It prevents the singularity. Think of trying to compress a piece of foam. You can squeeze it, but eventually the internal structure resists further compression with a powerful repulsive force. In loop quantum cosmology, the same principle applies to the universe. As the primordial cosmos is squeezed by its own gravity towards the Big Bang, the quantum nature of space itself generates a tremendous repulsion. Instead of collapsing into an infinitely dense point, the universe reaches a maximum density and then bounces. What we call the Big Bang is therefore the moment of rebound from a previous cosmic phase, a big bounce. In this model, there is no before in the classical sense, but there is a previous cycle. Our universe inherited its hot, dense state from the contraction of a predecessor, and the cycle could extend infinitely into the past. Beyond these geometric bounces, quantum theory offers another, even more exotic pathway for a universe to begin: creation from nothing. This isn't quite magic, it's a consequence of the inherent uncertainty that governs the quantum vacuum. Even in what we call empty space, there is a constant flickering of energy virtual particles popping in and out of existence. Now consider the universe as a whole. Under certain conditions, the entire cosmos could be treated as a quantum system. The transition from no universe to universe could be understood as a form of quantum tunneling. Imagine a ball resting in a valley. The valley represents the state of nothingness. To create a universe, the ball would need to be kicked up and over a huge energy barrier which seems impossible. Quantum tunneling provides a loophole. There is a small but finite probability that the ball can simply appear on the other side of the barrier without having to climb it. In this view, our universe tunneled into existence from a primordial quantum vacuum, a state of no space and no time, via a random fluctuation that was then locked in by a process like inflation. This event, while seemingly a true beginning, could itself be part of a larger, eternal cycle if the quantum vacuum is a perpetual state from which universes continually bubble forth. Each of these quantum gravity approaches paints a different picture of the pre-Big Bang universe, but they share a common, revolutionary implication. The Big Bang was very likely not the absolute beginning. Whether it was a bounce from a previous contraction, a phase transition in a higher dimensional reality, or a quantum fluctuation, it appears increasingly as an event within a much larger cosmic context. This fundamentally changes our understanding of time and existence. We are not living in a one-off universe with a definitive start date, but possibly in one chapter of an eternal story, a story without a first page. The quest for a theory of quantum gravity is therefore not just a technical exercise for physicists. It is a journey to answer the most profound question we can ask: where did we come from? And the emerging answer seems to be that we are part of a reality that has always existed, forever transforming itself in an endless dance of creation and renewal. This brings us to a principle that is as much about philosophy as it is about physics, one that directly addresses the incredible coincidence we find ourselves in. It's called the anthropic principle, and it offers a powerful way to think about why our universe seems so perfectly tailored for life. At its core, the principle is a simple statement of observational selection bias. We can only exist in a universe that has the right conditions to allow for our existence. It doesn't explain why the universe is the way it is, but it points out that we shouldn't be surprised to find ourselves in a cosmos that is hospitable. The constants of nature, the strength of gravity, the mass of an electron, the precise value of the cosmological constant, appear to be exquisitely fine-tuned. If any one of these numbers were even slightly different, atoms wouldn't be stable, stars wouldn't shine, and life as we know it would be impossible. In a single, one-off universe, this fine-tuning seems like a miracle, but in a cyclical or multiverse model, it becomes a statistical necessity. Now, connect this to the idea of a cyclical cosmos. If the universe undergoes endless cycles of birth, death, and rebirth, and if with each new cycle the fundamental constants are randomly reshuffled, then we have a mechanism for exploring every possible configuration of physics. The vast majority of these cosmic cycles would be stillborn, lasting only a fleeting moment or expanding into cold, empty voids where no complex structures could ever form. But given an infinite number of cycles, it becomes inevitable that a tiny fraction of them will, by pure chance, land on the specific combination of constants that permits the emergence of galaxies, stars, planets, and ultimately conscious life. We and our ability to ponder the nature of time loops are not the result of a deliberate design, but the product of a cosmic lottery that has been running for eternity. We exist in this particular cycle because it's one of the rare winners. This perspective casts a fascinating light on our own universe's properties, including its potential for being cyclical. Think about what a cycle requires. For a universe to be reborn, it needs a specific set of physical laws that allow for a transition from a contracting phase to an expanding one, whether through a quantum bounce, a brane-world collision, or another mechanism. A universe that simply expands forever into a heat death cannot loop. A universe that collapses too violently and quickly into a big crunch might not allow enough time for stars to form and life to arise. Therefore, a universe that is both habitable and cyclical might be an exceptionally rare and precious combination. The anthropic principle suggests that our observation of a universe capable of hosting us might inherently bias us towards also observing a universe that has the capacity for cyclicality. We are here to observe it precisely because this kind of stable, long-lived, complex-friendly cycle provides the extended timeline necessary for evolution to run its course. This leads to a profound implication. Our ability to even conceive of cosmological time loops might be a direct consequence of living in a universe that is, in fact, cyclical. The very laws of physics that allow for our existence might be the same laws that permit cosmic rebirth. The conditions that make life possible, a long-lasting, stable universe with stable atoms and energy sources like stars, are also the conditions that could be necessary for a cycle to complete. In this view, the fact that we are here to debate the issue is not separate from the evidence for the theory itself. It is part of the evidence. We are a product of the cycle, and our curiosity about our origins is the universe becoming conscious of its own potentially eternal nature. The anthropic principle, when combined with cyclical cosmology, transforms the question from "Why is the universe so perfectly suited for us?" to "What other kind of universe could we possibly find ourselves in?" The answer appears to be one that gives itself the gift of endless second chances. Returning to the world of string theory, we find a model that reframes the cosmic cycle not as a bounce, but as a direct universe-spanning impact. The ekpyrotic and cyclic model, which we introduced earlier, gains even more fascinating depth when we explore the specific string theory mechanics proposed to drive this grand collision. At its heart, this theory envisions our reality as a three-dimensional membrane, or brane, a vast sheet of existence adrift in a higher dimensional arena known as the bulk. This bulk space is not empty. It is a dynamic medium and floating parallel to our brain, separated by a microscopic distance in this unseen dimension, is another brain, another complete universe. The cosmic drama unfolds through a delicate dance of forces acting across this hidden gap. The driving forces of this cycle are a subtle interplay of attraction and repulsion. For most of the cycle, a mysterious form of energy, which we might identify as a type of dark energy, acts as a repulsive force, gently pushing the two branes apart. This phase corresponds to the expansion of our own universe that we observe today. As the branes separate, the space within them expands and cools, allowing galaxies to form and evolve over billions of years. But this repulsion is not the end of the story. An attractive force, perhaps mediated by fundamental strings that stretch across the bulk like invisible tethers, gradually gains strength. Over trillions of years, this attraction overcomes the repulsive push, and the two branes begin to approach one another. They don't simply drift together, they are drawn into a direct head-on collision. The kinetic energy of this impact is almost beyond comprehension. It is this colossal release of energy, transferred from the motion of the branes themselves, that manifests within our brain as the searing heat and dense particle soup of the Big Bang. In this view, the moment of creation is not an explosion from a point, but a uniform ignition across the entire surface of our reality, a flash of cosmic light born from contact. One of the most compelling aspects of this brane collision model is its potential to leave behind detectable evidence, a fossilized imprint of the event that birthed our cosmos. The violent collision of two such massive objects would not be a smooth, silent event. It would generate tremendous ripples in the fabric of spacetime itself, gravitational waves. But these wouldn't be the high-frequency waves we detect from merging black holes today. The collision would have created a background sea of primordial gravitational waves, stretching across the entire universe with incredibly long wavelengths. The search for this signal is one of the most active frontiers in cosmology. Experiments like space-based gravitational wave observatories are designed to listen for the faint echo of this ancient impact. Finding this specific pattern in the gravitational wave background would be a smoking gun, strong evidence that our universe began not with a solitary bang, but with a resonant crash. Furthermore, the precise nature of the collision could have shaped the large-scale structure of the cosmos in unique ways. The initial distribution of matter and energy, imprinted by the collision, might have created subtle statistical fingerprints in the way galaxies are clustered across the sky. While the cosmic microwave background appears remarkably uniform, ultra-precise maps of the distribution of millions of galaxies could reveal faint, wispy patterns, anisotropies, that are characteristic of a brane collision rather than a traditional inflationary expansion. The quest to find these signatures is like trying to distinguish the unique crackle of a specific type of fire from the general sound of burning. It requires incredible sensitivity and a deep understanding of what to listen for. If such a signature were ever confirmed, it would fundamentally rewrite our cosmic origin story, pointing toward a universe born from a cyclical, multidimensional encounter. But to truly appreciate how our universe might loop back on itself, we must confront its most dominant and most mysterious constituents. We've mapped the stars and galaxies, but this luminous matter accounts for less than 5% of the cosmos. The overwhelming majority is comprised of two invisible entities, dark matter and dark energy. Their names betray our ignorance, yet these enigmatic forces may hold the master key to the cosmic cycle, acting as the ultimate architects of eternal return. Their interplay, a grand cosmic tug of war between attraction and repulsion, could dictate not just the fate of our universe, but its potential for rebirth. For decades, we've known that dark matter exists because of its gravitational pull. It's the invisible scaffolding that holds galaxies together. Without its immense gravitational influence, galaxies would fly apart as they spin. Dark matter provides the cosmic glue, the attractive force that works to pull the universe back together. Dark energy, discovered much more recently, is its perfect opposite, a mysterious pressure infused within the fabric of space itself, causing the expansion of the universe to accelerate. It is the ultimate repulsive force, pushing galaxies apart at an ever-increasing rate. The history of our cosmos has been a battle between these two titans. In the early universe, when matter and energy were densely packed, gravity ruled, slowing the expansion. But as the universe grew more diffuse, dark energy's push overcame gravity's pull, leading to the accelerated expansion we see today. The conventional view is that dark energy has won, dooming the universe to an eternal, cold expansion. But what if this victory is only temporary? One compelling cyclical model suggests that dark energy is not a constant, immutable force. Instead, it could be a dynamic field, often referred to as quintessence. Imagine it not as a steady push, but as a fuel that is slowly burning off. In this scenario, the accelerated expansion we observe is just a phase. Over trillions of years, the energy density of this quintessence field could gradually decay, weakening its repulsive power. As it fades, gravity, primarily from the vast, unseen networks of dark matter, would begin to reassert its dominance on a cosmic scale. The expansion of the universe would slow, then halt, and finally reverse. Galaxies would start rushing back toward one another, drawn by the relentless pull of dark matter's gravity, eventually leading to a catastrophic Big Crunch. This crunch, in turn, could create the conditions for a new Big Bang. In this model, the cycle is a slow, cosmic pendulum swing, driven by the changing strength of dark energy against the constant, patient pull of dark matter. But dark matter itself might play a more active role than just providing gravitational ballast. Some theoretical models propose that dark matter is not entirely stable. What if it can decay? Over inconceivably long timescales, dark matter particles could slowly transform into lighter particles, releasing energy in the process. This decay would subtly alter the universe's energy budget. Alternatively, dark matter might have properties we haven't yet imagined. It could interact with itself through a dark force, or even undergo a phase transition, much like water freezing into ice under the extreme conditions of the far future. Such a phase transition could fundamentally reshape the vacuum of space, releasing a colossal amount of energy. This sudden injection of energy could act as a cosmic reset button, potentially reigniting a new inflationary epoch or triggering a phantom energy collapse where the expansion violently reverses. In these scenarios, dark matter isn't a passive participant. It's the dormant agent of change, its hidden transformations setting the stage for the next act in the cosmic drama. The beauty of these theories is that they are, in principle, testable. If dark energy is quintessence and not a true cosmological constant, its strength should change over time. The next generation of telescopes, like the Nancy Grace Roman Space Telescope and the Extremely Large Telescope, will make incredibly precise measurements of the expansion rate of the universe across cosmic history. By tracking how the acceleration has changed over billions of years, we could detect the faintest hint that dark energy is weakening, providing the first observational clue that a cyclical fate might await us. Similarly, experiments deep underground and in space are tirelessly searching for any non-gravitational interactions of dark matter. Discovering that dark matter can decay or self-interact would open up a universe of possibilities, including those that point toward a cyclical cosmos. The very mysteries that currently perplex us, the nature of the dark universe, may ultimately reveal that the story of existence is not a linear tale with a single beginning, but an eternal epic written in the invisible ink of dark energy and dark matter. But to truly grasp a universe that might be fundamentally mathematical in nature, we must shift our perspective from the physical to the abstract. This brings us to a hypothesis so audacious it borders on the philosophical, proposed by physicist Max Tegmark. It's called the mathematical universe hypothesis, and it suggests that our physical reality isn't just described by mathematics, it is mathematics. In this view, the cosmos isn't a machine made of matter and energy operating according to mathematical rules. Instead, it is the mathematical structure itself, and we are self-aware patterns within that structure. When we apply this radical idea to the concept of time loops, the implications become even more profound. A cyclical universe wouldn't be a physical mechanism of bounces or collisions, but an inherent logical property of the specific mathematical equation that defines our existence. To understand this, consider a simpler mathematical object like a circle. A circle has no beginning and no end. It is an infinite loop. Its existence and properties are entirely defined by its mathematical description. Now imagine a vastly more complex mathematical structure, one that encodes not just a shape but space, time, particles, forces, and the laws of physics. According to Tegmark, our universe is exactly that, a specific, self-consistent mathematical structure. The Big Bang and the entire 14 billion-year history that followed wouldn't be a physical event unfolding in time, but a necessary, logical consequence of the structure's properties, much like the angles of a triangle must add up to 180 degrees. If this overarching mathematical structure is inherently cyclic, if it describes a closed time-like curve on a cosmic scale, then a time loop is not just possible, it is inevitable. The first loop wouldn't be a moment in time because time is part of the structure. It would simply be the logical starting point from which the structure's properties unfold, and if it is cyclic, eventually fold back upon themselves. This perspective completely reframes the question of why the universe exists. In most physical models, we seek a cause, a quantum fluctuation, a brane collision, a bounce. But in the mathematical universe hypothesis, the question is almost meaningless. A mathematical structure doesn't happen, it just is. It exists in a timeless, placeless realm of mathematical possibility. Our experience of a flowing, linear time is simply our consciousness moving through a particular subset of this static mathematical structure. The entire cosmic cycle, from bang to crunch and back again, would be an eternal, unchanging truth, much like the number pi. We perceive it sequentially because we are embedded within the structure, but from an outside perspective, if such a thing could exist, the entire cycle would be present at once, a completed mathematical object. This leads to a staggering corollary. If all mathematical structures exist in a Platonic sense, then our universe is not special. It is just one of an infinite ensemble of mathematical realities. Some of these structures would be simple, describing empty universes with only a handful of dimensions. Others would be incredibly complex, with physics utterly alien to our own. And a vast number of them would be cyclical. In this ultimate multiverse, every conceivable cosmic story is being told, not in a physical space, but in the abstract landscape of mathematics. We find ourselves in this particular mathematical structure, this particular universe, simply because it is one of the structures complex enough to contain self-aware substructures like us who can observe it. This is the ultimate anthropic principle. We don't observe a universe with mathematical properties that allow for our existence. We are patterns within a mathematical structure that inherently supports complex, self-aware patterns. The hypothesis also offers a unique take on the fine-tuning problem. Why do the fundamental constants seem so perfectly calibrated for life? Tegmark's answer is that these constants aren't dials that were randomly set. They are fixed, necessary properties of the specific mathematical structure we inhabit, just as the ratio of a circle's circumference to its diameter is fixed by the definition of a circle. We shouldn't be surprised that the constants allow for life. We should only be surprised that we exist within a structure that allows for us to be surprised. A cyclical nature could be another such fixed property. The fact that our universe might be on a loop could be as fundamental to its identity as the number 3 is to the structure of a triangle. Searching for evidence of this cycle, then, becomes a process of discovering the deeper mathematical symmetries that govern our reality, looking for the fingerprints of a closed, self-contained equation in the patterns of the cosmos. Shifting our focus from abstract mathematics to a process that feels strangely familiar, we arrive at a theory that applies the most powerful idea in biology to the cosmos itself. This is Lee Smolens's theory of cosmic natural selection, a breathtaking concept that suggests universes evolve. Just as plants and animals evolve through natural selection on Earth, entire cosmic realms might be subject to a similar process of variation, selection, and reproduction. In this grand vision, the multiverse becomes a cosmic ecosystem, and the ultimate goal of a universe isn't to harbor life, but to produce as many black holes as possible. The engine of this cosmic evolution is the black hole. Smolens's radical proposal is that every time a black hole forms in our universe, it doesn't lead to a singularity in the classical sense. Instead, the immense compression and violence of a collapsing star or a galactic core collapse triggers a quantum gravitational phenomenon that gives birth to an entirely new universe, hidden from our view within the event horizon. This new universe expands into its own dimensions with its own set of physical laws. But here's the crucial twist. The laws of physics in the offspring universe are not an exact copy of the parents. They are slightly mutated, much like the genetic code of an offspring has small, random variations. The strength of gravity, the mass of electrons, the cosmological constant, these fundamental numbers could be randomly tweaked in the birthing process. This simple mechanism sets the stage for a form of cosmological Darwinism. Imagine a population of universes, each with different physical constants. Some universes might have a gravitational force so weak that matter can never clump together to form stars, let alone the dense cores needed for black holes. These universes would be evolutionary dead ends. They would produce no offspring. Other universes might have physics so violent that they collapse back on themselves almost instantly in a big crunch, again leaving no time for black holes to form. But a small fraction of universes will, by chance, have the perfect Goldilocks conditions for prolific black hole production. They need stable, long-lived stars that can fuse heavy elements and then explode as supernova, leaving behind neutron stars and black holes. They need the right conditions for galaxies to form and for massive black holes to merge in their centers. These universes, the ones that are finely tuned for making black holes, will be the most reproductively successful. Over countless generations, the multiverse would become dominated by universes that are excellent at making black holes, simply because they are the ones having all the babies. This is where the potential for a time loop enters the picture as a rare and powerful mutation. In Smolin's framework, the specific laws of physics are what evolve. A cyclical universe, one that can bounce from a big crunch to a new big bang, could be seen as one such possible set of laws. At first glance, a universe that simply cycles might not seem to have a reproductive advantage over one that expands forever and produces black holes. But consider the long-term prospects. A linear universe has one finite timeline to produce all its black holes before it succumbs to heat death. A cyclical universe, however, gets an infinite number of chances. With each new cycle, it can produce another entire crop of black holes. Over an eternal timescale, a cyclical universe could potentially produce vastly more offspring than any linear universe could in its single, finite lifetime. Therefore, a time loop wouldn't just be a curious feature. It could be a supreme adaptation in the struggle for cosmic existence. If this particular mutation, the law of physics that allows for a cyclical rebirth, ever arises randomly in a universe, that universe could have a monumental reproductive advantage. Its lineage would not die out but would perpetuate itself indefinitely, each cycle birthing countless new universes through its black holes, some of which might inherit the cyclical trait. In this scenario, the reason we might find ourselves in a universe capable of such a cycle is not because it's necessary for us, but because cyclical universes are, in the grand Darwinian competition of the multiverse, the ultimate survivors. Our very existence could be a byproduct of our universe's success in a never-ending cosmic replication race. Now we arrive at a theory that turns our conventional experience of time completely on its head, proposing that the arrow we feel so intrinsically is not a one-way street at all, but a two-lane cosmic highway. This is physicist Julian Barber's theory of shape dynamics and the Janus point, a radical reimagining of the universe that dispenses with the idea of a beginning entirely. Barber invites us to consider time not as a fundamental river flowing from past to future, but as an emergent property, a side effect of the universe's changing configuration. At the heart of this idea is a moment of ultimate simplicity, a state Barber calls the Janus point, named after the two-faced Roman god of beginnings and endings. This point is the Big Bang, but not as a creation event. Instead, it is the central pivot of a perfectly symmetric cosmos. To grasp this, imagine the entire universe as a collection of all the particles and their positions relative to one another. This total configuration is what Barber calls a shape. The universe's history is simply a sequence of these shapes, one after another. Now, what if this sequence of shapes displayed a special kind of symmetry? Picture a perfectly symmetrical movie reel. It starts with a single, simple frame at the center, the Janus point. As you run the film forward from that center, the shapes become increasingly complex. Particles move apart, galaxies form, stars ignite, and life emerges. This is the arrow of time as we know it, moving toward increasing complexity and what we perceive as the future. But here's the extraordinary part. If you run the film backward from that same central frame, an identical process unfolds. The universe becomes larger and more complex in that direction as well. From our perspective, living on one side of the Janus point, the other side appears as a universe collapsing into a big bang. But from the God's eye view of shape dynamics, there is no collapse. There are simply two expanding, evolving universes emerging from a common root, like two trees growing in opposite directions from a single seed. This model offers an elegant solution to one of physics' most perplexing problems. Why did the Big Bang have such an incredibly low entropy? In standard thermodynamics, the low entropy of the early universe is a bizarre, special initial condition that demands an explanation. In Barber's two-way time model, it is not an initial condition at all. It is a natural consequence of the geometry of the cosmos. The Janus point is the moment of minimum complexity and maximum symmetry. It is the simplest possible shape the universe can have. As we move away from it in either direction of the film reel, complexity and disorder, entropy naturally increase. There is no need to explain a low entropy start because there is no start. The universe simply has a middle, a point of balance from which complexity grows in two temporal directions. The arrow of time we experience is not an absolute feature of the cosmos. It is a local perspective, a result of our position on one particular branch of this double-sided structure. The implications for a cyclical universe are profound. The Janus point itself could be the pivotal moment in a much larger cycle. Instead of a linear sequence of universes, we might have a chain of these double-sided cosmic epochs. Imagine one of the expanding branches eventually reaching a state of maximum complexity and then, through some physical process we've yet to understand, finding its way back to another Janus point, another moment of ultimate simplicity. This new Janus point would then become the origin for another pair of expanding universes. In this grander vision, reality would resemble an endless chain of hourglasses, each Janus point being the narrow waste where the sand passes through, giving rise to two new bulbs of spacetime. Our entire cosmic history, from the Big Bang to the far future, would be just one half of one link in this magnificent, timeless chain, a cycle where every ending is also a beginning, and every beginning is simply a turning point in an eternal dance of shapes. Now, let's distill the cosmos down to its most minimal essence, to a concept that seems to defy common sense, something from nothing. This is the theory that our entire universe could be the ultimate free lunch, a spontaneous quantum fluctuation in a perfect, featureless void. The idea hinges on a subtle but crucial principle of quantum mechanics. Absolute stillness is impossible. Even in a state we would call a true vacuum, a complete and total absence of particles and fields, there is a fundamental fuzziness, an inherent uncertainty governed by the Heisenberg principle. This allows for tiny, fleeting violations of energy conservation. Particle-antiparticle pairs can pop into existence, borrowing energy from the vacuum for an infinitesimally brief moment before annihilating and paying the energy back. What if, in the unfathomable reaches of eternity, a fluctuation occurred that was not so tiny? What if a bubble of space-time, complete with its own laws of physics, fluctuated into existence and, through a mechanism like inflation, was caught and stabilized, growing exponentially into the cosmos we see today? In this view, the Big Bang wasn't an explosion in a pre-existing space. It was the sudden, spontaneous genesis of space, time, and matter from a literal nothingness. The leap from a virtual particle pair to an entire universe is, of course, astronomically improbable, but quantum mechanics deals in possibilities, not certainties. Given an infinite amount of time, or more precisely, in the context of a timeless void, even the most unlikely event becomes not just possible but inevitable. The universe's initial low entropy state, which we've seen is so puzzling, would in this model be a consequence of its origin from the ultimate simplicity of nothing. The challenge, however, is turning this one-time event into a cycle. For that, we need to consider the universe's ultimate fate. If the prevailing dark energy leads to an eternal, accelerating expansion, the cosmos will eventually approach a state that is, for all intents and purposes, a new kind of nothing, a cold, dark, empty vacuum stretched so thin that all activity ceases. It's a return to a featureless state, albeit a much larger and colder one than the primordial void from which it sprang. This is where the cycle emerges. If the universe can return to a vacuum state, then the same quantum rules that allowed for its initial birth remain in effect. Over timescales that dwarf trillions upon trillions of cosmic lifetimes, the quantum vacuum is not truly dead. It is a seething potentiality. The improbable can happen again. A new quantum fluctuation could ignite a new bubble of inflation, birthing a fresh universe within the decaying corpse of the old one. This new cosmos would be entirely disconnected from ours, with its own random set of physical constants, blooming into existence entirely on its own. The cycle isn't a rhythmic pulse of one universe rebooting. It's a sporadic, statistical process. Universes would pop into existence at random intervals across an eternal meta-time, each one living out its linear history before fading back into the void, waiting for the next random genesis. This creates a fascinating concept, a multiverse in time. Unlike the traditional multiverse, where an infinite number of universes exist simultaneously in a vast spatial landscape, this model presents a sequence of universes existing one after the other along a temporal axis. There is only one universe at a time, but over eternity, every possible universe will eventually come into being. It's a cosmic cinema where only one film is ever playing, but the reel contains every movie that could ever be made, each one projected in a random order across an infinite timeline. The probability of a universe like ours, with its specific constants and long lifetime, might be vanishingly small, but given an infinite number of rolls of the quantum dice, it was bound to happen. Our existence isn't a miracle, it's a statistical certainty over a sufficiently long duration. This model offers a profound, if humbling, perspective. We are not living in a special universe, but merely in a fortunate one, a rare but inevitable flicker of order in an endless, silent darkness punctuated by similar, isolated flashes of cosmic light. All the theories we have explored so far share a common feature. They place humanity, and indeed all conscious life, in the role of a passive passenger. We are merely along for the ride on a cosmic journey whose course is set by impersonal forces of physics, whether they be quantum bounces, colliding brains, or holographic resets. But what if our role is not so passive? What if observers are not a late-stage byproduct of cosmic evolution, but an essential, active ingredient in the very reality of the universe? This is the profound and mind-bending proposition of physicist John Wheeler's participatory anthropic principle, an idea that pushes the relationship between consciousness and cosmos into entirely new territory. The standard anthropic principle, which we discussed earlier, is a statement of observational selection. We find ourselves in a universe suited to life because we couldn't exist in one that isn't. It's a principle of passive coincidence. Wheeler's participatory version is far more radical. It suggests that observers are necessary to bring the universe into being, that reality is not truly real until it is observed. To grasp this, we need to step into the strange world of quantum mechanics, which was Wheeler's playground. You may have heard of the famous double-slit experiment, where a single particle like an electron seems to pass through two slits at once, behaving like a wave and creating an interference pattern on a detector screen. This wave-like behavior suggests the particle takes all possible paths simultaneously, a state known as a superposition. However, the moment you place a detector at one of the slits to see which path the electron actually takes, the superposition collapses. The electron suddenly behaves like a single particle, choosing one definite path, and the interference pattern vanishes. The act of measurement, of observation, seems to force the fuzzy cloud of quantum possibilities to resolve into a single, concrete reality. Wheeler took this a dramatic step further with his delayed choice thought experiment. Imagine a particle that has already traveled from a source through the slits and is well on its way to the detector. Even after the particle has supposedly chosen its path, Wheeler showed that the experimenter's decision of how to measure it, whether to observe the path or to look for interference, can retroactively determine how the particle behaved in the past. It's as if the present act of observation reaches back in time and tells the particle what it should have been doing all along. Wheeler famously used the analogy of a game of 20 questions, but with a surprising twist. Imagine you leave the room while the players decide on a word. You return and start asking yes or no questions to guess the word. After a long series of questions, you finally guess the word, say, cloud. But then the players reveal a secret. They hadn't agreed on a word beforehand. They simply decided that each answer would be consistent with the previous ones, but they would wait until the very last moment to choose a word that fit all the answers given. The reality of the word cloud was not predetermined. It was brought into existence by the questions you asked. For Wheeler, the universe is like that. The questions we ask through our experiments and observations participate in determining the answers, in bringing a specific reality into focus from a haze of quantum potentiality. In his own poetic words, we live in a participatory universe. Now, let's weave this extraordinary idea into the fabric of a cyclical cosmos. If the universe requires participants to actualize its reality, then a cycle that simply repeats identically might be incomplete. The universe might need to evolve conscious observers not as an accidental byproduct, but as a fundamental part of its operational logic. Each cosmic cycle could be seen as a process whose ultimate goal is to create the conditions necessary for observers to emerge. These observers, through the cumulative act of observation of measuring the cosmos, from gazing at the stars to smashing particles in accelerators, would gather the information needed to define the universe's state. This act of collective observation could be what allows the cycle to culminate, providing the necessary data or meaning that triggers the transition to the next cycle. The Big Bang would not just be a physical event, it would be a moment of cosmic resolution, a universe having achieved self-awareness and, in doing so, fulfilling the condition for its own rebirth. This creates a breathtakingly elegant closed loop. The universe begins in a hot, dense state, expanding and cooling over billions of years to form galaxies, stars, and planets. On at least one such planet, life emerges and evolves into conscious beings capable of looking back at the universe and questioning its origins. These observers, through their scientific and philosophical inquiries, gradually measure and define the properties of their reality. This long, slow process of cosmic self-awareness reaches a critical mass, perhaps at the universe's maximum state of complexity, just before its final descent into heat, death, or collapse. This culmination of observation then acts as the seed for the next Big Bang, not in a physical sense, but in an informational one. The universe that is observed is the universe that is reborn. In this model, we are not just living in a time loop, we are active participants in its very continuity. Our curiosity about the cosmos is not a trivial pastime. It is a fundamental cosmic function, a necessary step in an eternal cycle of reality defining itself through the emergence of life and mind. This perspective offers a startling answer to the question of why the universe is comprehensible at all. Why do mathematics and logic, products of the human mind, so perfectly describe the laws of nature? The participatory anthropic principle suggests it is because the mind and the cosmos are part of a single, self-consistent loop. The universe is comprehensible because it has been, in some sense, structured by the process of comprehension. We are the universe's way of understanding itself, and in that act of understanding, we complete a circuit that allows the whole magnificent process to begin anew. It's a vision of cosmos and consciousness inextricably linked, forever dancing in a loop of mutual creation, where every ending is a new beginning born from the act of looking back. Yet if information can never be destroyed, its ultimate fate presents a fascinating puzzle, especially when we consider the end of our universe. The holographic principle offers a compelling solution, suggesting that the information isn't lost because it was never truly confined within the three-dimensional volume in the first place. Instead, it remains eternally encoded on the two-dimensional boundary of our cosmos. As our universe expands toward heat death, this cosmological horizon becomes a vast, cold, and silent library, its surface crammed with the maximum possible amount of information, a complete, bit-for-bit blueprint of every galaxy, star, planet, and person that ever existed. This dormant data shell, this fossilized record of a universe lived, could become the most fundamental ingredient for a cosmic cycle. A cyclical model, in this context, isn't just about matter and energy being recycled. It becomes a cycle of information being read out and rewritten. The transition from one universe to the next could be a process where the information on the boundary of the old, dead cosmos is reprocessed, acting as the initial conditions for a new Big Bang. The two-dimensional data is translated back into a new, hot, dense, three-dimensional reality. In this view, each cycle inherits the essential memory of the previous universe in its fundamental parameters, while the specific historical details, the exact arrangement of galaxies or the rise and fall of civilizations, might be scrambled or reset, like a hard drive being reformatted for a new operating system. This provides a deeply elegant mechanism for eternal return, where the universe is not just in a loop of space and time, but in a loop of information itself, forever encoding and decoding its own existence on the boundary of reality. This idea of information conservation forcing a cyclical cosmos finds a startling parallel in one of the most famous paradoxes in physics, the black hole information paradox. The puzzle begins with Stephen Hawking's realization that black holes evaporate over astronomical timescales. If a book falls into a black hole, all the information contained in its pages seems to be lost forever when the black hole finally radiates away, violating the core quantum principle that information must be preserved. The holographic principle resolves this by stating the information isn't inside the black hole, it's encoded on its event horizon. Now, scale this idea up to the entire universe. If our observable cosmos has a horizon, and if that horizon holds a holographic description of everything within it, then the evaporation of our universe into heat death isn't an information-destroying event. It's simply the universe reaching its final, stable data state. The paradox only arises if we assume this is the absolute end. But if that information-laden horizon can serve as the seed for a new universe, the paradox vanishes. The information is conserved not by being hidden, but by being used again. The cyclical model becomes the universe's own solution to its greatest informational challenge, ensuring that nothing, not a single quantum bit of our cosmic history, is ever truly lost, only transformed and reborn in a new cosmic iteration. Now, let's shift our perspective from the grand collisions of brains and the cosmic recycling of information to a transformation that might feel surprisingly familiar from everyday life. Imagine taking an ice cube out of the freezer and placing it in a warm room. Slowly, it melts into a puddle of water. Now, imagine reversing the process, cooling that water until it crystallizes back into solid ice. This change from one state of matter to another is a phase transition, a fundamental reorganization of a system's properties. What if the birth of our universe was not a violent explosion from a singular point, but a cosmic-scale phase transition? This is the compelling idea behind our 24th theory, which reimagines the Big Bang as a moment when the very fabric of reality underwent a sudden and dramatic shift, like water freezing or boiling, forever altering the nature of existence. To grasp this, we need to think about the universe not as empty space, but as filled with an invisible energy field, often called the vacuum field. The term vacuum is misleading. We think of it as nothing, but in quantum field theory, the vacuum is seething with potential energy. It's the lowest possible energy state a region of space can have, but crucially, it might not be the only possible lowest energy state. Think of it like a landscape of hills and valleys. A ball resting at the bottom of a deep valley is in a stable, low-energy state. But what if there's an even deeper valley nearby, separated by a high hill? The ball in the first valley is stable, but not absolutely stable. It's in what physicists call a false vacuum. Given a big enough nudge or through a random quantum fluctuation, it could tunnel through that hill and roll down into the deeper, more stable valley. This transition from a higher energy false vacuum to a lower energy true vacuum would release a colossal amount of energy. This, theorists propose, is the essence of the Big Bang. Our universe began when a patch of a primordial, high-energy false vacuum underwent a phase transition, decaying into a lower energy state and releasing the immense latent heat that became all the matter and radiation we see today. This framework elegantly sidesteps the thorny problem of the singularity. Instead of an infinitely dense, infinitely hot point where the laws of physics break down, the Big Bang becomes a well-defined physical process, a cosmic change of state similar to boiling. The universe didn't appear from nothing. It transformed from one type of something, an unstable, high-energy vacuum state, into another, more stable something that we recognize as our familiar spacetime, complete with particles and forces. This process, known as bubble nucleation, would have started in a tiny region. A bubble of the new, true vacuum would form and then expand outward at nearly the speed of light, its wall a fiery front of released energy. Our entire observable universe could be the interior of one such bubble, a domain of stable vacuum within a much larger, still inflating meta-universe that remains in the false vacuum state. This naturally leads to a breathtaking possibility for a cyclical cosmos. What if the vacuum state our universe resides in isn't the final destination? What if our true vacuum is, in the grand scheme of things, just another false vacuum resting in a valley that is deep but not the deepest? Over cosmological timescales, trillions of years in the future, a new quantum fluctuation could trigger another phase transition. Our entire universe, or a region of it, could suddenly decay into an even lower energy vacuum state. This wouldn't be a slow fading, it would be an instantaneous, catastrophic event. The fundamental constants of nature, the strength of forces, the masses of particles would change in a flash. Atoms would disintegrate, matter as we know it would cease to exist, and the universe would be reborn under a completely new set of physical laws. In this model, the cycle isn't a bounce or a collision, but a series of these vacuum decays. The cosmos would oscillate between different vacuum states, each transition marking the end of one cosmic era and the violent, transformative beginning of the next. Each new vacuum would be a blank slate with its own unique physics, some perhaps lasting only moments, others enduring long enough to give rise to complexity and life, all within an eternal sequence of cosmic metamorphosis. But to truly challenge our intuitive sense of a flowing, linear time, we must turn to one of the most well-established theories in all of physics, Einstein's special relativity. This theory doesn't just describe the universe, it fundamentally redefines our understanding of time itself, leading to a concept known as the block universe. In this view, the distinction between past, present, and future is not a fundamental reality, but a persistent illusion of our consciousness. Special relativity tells us that the rate at which time passes is not absolute. It depends on an observer's motion and gravitational field. If you were to travel away from Earth at a significant fraction of the speed of light and then return, you would find that less time has passed for you than for everyone you left behind. This time dilation effect is not a theoretical curiosity. It is a measurable reality confirmed by experiments with atomic clocks on airplanes and satellites. The shocking implication is that there is no universal now. What is the present moment for you might be the past for a rapidly moving astronaut and the future for someone in a strong gravitational field. There is no single, privileged clock ticking for the entire cosmos. This relativity of simultaneity shatters the classical idea of a flowing river of time. If we cannot define a universal present, then how can we say that the past is gone and the future is yet to be? Einstein himself grasped this profound conclusion, writing in a letter of condolence after the death of a friend. Now he has departed from this strange world a little ahead of me. That means nothing. People like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion. This insight gives rise to the philosophy of eternalism, which posits that past, present, and future are equally real. All moments in time, the birth of the universe, the fall of the Roman Empire, your reading of this sentence, and the heat-death of the cosmos all exist simultaneously and eternally. Reality is not a succession of fleeting nows. It is a static, four-dimensional block where time is simply another dimension, much like the three dimensions of space. Imagine the entire history of the universe as a finished movie on a DVD. The DVD contains every scene from the opening credits to the final frame. When you play the movie, your consciousness is like the laser in the DVD player, moving sequentially from one frame to the next, creating the illusion of a story unfolding in time. But the entire story is already there, complete and unchanging. In the block universe, we are not the creators of the movie, we are characters within it, and our conscious awareness is simply scanning along the timeline, giving us the powerful but mistaken impression that the future is open and the past is fixed. In reality, from a God's-eye perspective outside the block, everything just is. This eternalist picture completely reframes our discussion of cosmological time loops. If the entire timeline of the universe is a fixed, four-dimensional object, then a loop in time is not a process that happens within time. It is not a sequence of events that repeats. Instead, it is a topological feature of the block itself, a closed curve woven into the fabric of spacetime. Think of it like a knot in a piece of wood or a loop drawn on a piece of paper. The loop doesn't happen, it simply exists as a geometric property. In this context, the first-time loop is a meaningless phrase. There is no first iteration because the loop is not being traversed repeatedly. It is a single, eternal structure. If you were to follow the timeline of the universe through one full cycle, you would eventually find that it connects back to itself, forming a closed time-like curve. Our experience of living through the cycle would feel linear and sequential, but in the grand architecture of the block universe, we are simply traveling along a pre-existing circular path. This perspective offers a radical solution to some of the paradoxes that plague other time loop theories. For instance, the classic grandfather paradox, where you travel back in time and prevent your own birth, seems logically impossible. But in the block universe, the timeline is fixed and self-consistent. Any attempt to change the past would have already been part of the timeline all along. Your journey to the past and your actions there are already written into the four-dimensional block. The universe would conspire through seemingly random events to prevent a true paradox. Perhaps your gun jams, or you miss your target, or you discover that the man you thought was your grandfather wasn't actually your biological grandfather. The loop is a single, coherent story where the end is connected to the beginning in a logically consistent way. There are no multiple iterations or resets. There is only one eternal loop, and our lives are our unique, one-time journey along its path. The block universe and eternalism provide a starkly beautiful and humbling vision of reality. It suggests that free will, as we commonly understand it, might be an illusion. Our choices feel real, but from the perspective of the completed block, every decision we will ever make is already a part of the cosmic structure. This is not a cause for despair, but an invitation to see ourselves as integral parts of a vast, timeless whole. Our journey through the loop, with all its triumphs and tribulations, is a necessary and eternal feature of the cosmos. We are not temporary visitors in a flowing time. We are permanent inhabitants of an eternal now, forever etched into the geometric shape of the universe. The search for the first-time loop transforms from a quest for a starting gun into an exploration of the universe's ultimate, unchanging geometry. Now, to uncover a potential mechanism for a truly smooth and stable cosmic cycle, we venture into a theory that represents one of the most sought-after extensions of the standard model of particle physics. This is the principle of supersymmetry, often abbreviated as SUSY, a majestic mathematical symmetry that proposes a profound and elegant partnership at the heart of reality. At its core, supersymmetry suggests that for every known fundamental particle, the quarks, electrons, and photons that build our world, there exists a hidden supersymmetric partner. For every particle of matter, a fermion, there should be a partner particle of force, a boson, and vice versa. An electron would have a partner called a selectron, a quark a squark, and the photon would be paired with a photino. This concept isn't just about cosmic bookkeeping. It's a theoretical powerhouse that could solve several deep puzzles in physics, and crucially, it might provide the perfect ingredients to stabilize a universe destined for eternal return. The connection to a cyclic cosmos lies in one of supersymmetry's most celebrated potential benefits, taming the vacuum energy. You see, according to quantum field theory, the empty space of the vacuum is not truly empty. It's a seething sea of virtual particles constantly flickering in and out of existence. Each of these fluctuations contributes a tiny amount of energy, and when you add up all these contributions from all known particles, the result is a catastrophic number. The predicted energy density of the vacuum should be enormous, around 120 orders of magnitude larger than what we actually observe from the accelerated expansion driven by dark energy. This is the infamous cosmological constant problem, often called the worst prediction in the history of physics. Supersymmetry offers a breathtakingly elegant solution. In a perfectly supersymmetric world, the contributions of standard particles to the vacuum energy would be exactly cancelled out by the contributions of their superpartners. The positive energy from one set would be perfectly balanced by the negative energy from the other, driving the net vacuum energy to zero. This delicate cancellation could create the stable, flat vacuum landscape necessary for a long-lasting and predictable cosmic cycle, preventing the universe from tearing itself apart or collapsing prematurely. But how does this relate to a bounce? To understand that, we need to consider what happens when we apply supersymmetry not just to particles, but to the entire history of the universe. Some cosmological models that incorporate supersymmetry, particularly those arising from superstring theory, suggest that the transition from a contracting phase to an expanding one, the Big Bounce, could be a much gentler affair than previously imagined. In a non-supersymmetric model, the universe collapsing toward a big crunch would become incredibly hot and chaotic. Quantum fluctuations would run wild, and the geometry of spacetime would become a turbulent, unpredictable foam. Passing through such a state to emerge as a smooth, orderly universe like our own seems nearly impossible. It would be like expecting a shattered pane of glass to reassemble itself into a perfect window. Supersymmetry, however, can act as a cosmic stabilizer. The presence of the superpartner particles imposes powerful constraints on the kinds of quantum fluctuations that can occur. It effectively softens the physics at extremely high energies, suppressing the wildest fluctuations and preventing spacetime from descending into total chaos. This opens the door for a non-singular bounce. Instead of the universe collapsing to an infinitely dense point where all laws of physics break down, the repulsive forces generated by supersymmetric quantum effects could kick in at a finite maximum density. Think of it as a universe equipped with the ultimate shock absorption system. As contraction reaches its peak, the supersymmetric properties of the vacuum generate a powerful yet smooth repulsive pressure. This pressure doesn't cause a violent explosion, but rather a graceful reversal, like a cosmic dancer pushing off from the floor. The universe transitions from contraction to expansion without ever passing through a lawless singularity. The immense heat and density of the bounce are simply a natural consequence of the compression, but the process itself is orderly and governed by well-defined physical laws throughout. In this picture, the Big Bang is not a beginning from nothing, but a moment of cosmic turnaround within an eternal, supersymmetric cycle. The implications of such a smooth bounce are profound for the structure we see in our universe today. In the standard inflationary Big Bang model, the seeds for galaxies are planted by random quantum fluctuations during a brief period of hyper-fast expansion. A supersymmetric cyclic model offers a compelling alternative. Because the bounce is non-singular and the physics remains well-behaved, the quantum fluctuations that existed in the contracting phase of the previous universe can be faithfully transmitted through the bounce. The large-scale structures, the gravitational whispers of galaxies and clusters from the previous cycle, would not be erased by a violent singularity. Instead, they would be imprinted onto the newborn, expanding universe, providing the initial density variations that would later grow under gravity into the cosmic web we observe. Our universe, in this view, may carry the faint, fossilized imprint of a cosmos that existed before our own, its history woven into the very fabric of the gravitational field that shapes the night sky. While direct evidence for supersymmetry remains elusive in particle colliders like the Large Hadron Collider, its potential role in crafting a stable, cyclical cosmos presents a powerful theoretical motivation for its existence, suggesting that the symmetry might be hidden not in the particles we see today, but in the deepest architecture of spacetime itself. What if our universe is not a vast, lonely island, but a bridge, a cosmic tunnel connecting two separate realities in a grander, higher dimensional landscape? This is the staggering proposition of our next theory, which reimagines the entire cosmos as the interior of a giant quantum wormhole. To grasp this, we need to first understand what a wormhole is in the context of general relativity. Often called an Einstein-Rosen bridge, a wormhole is a hypothetical shortcut through the fabric of spacetime, a tunnel with two mouths connecting distant points that would otherwise be impossibly far apart. Now take this concept and inflate it to a literally universal scale. Instead of a tunnel you could fly a spaceship through, imagine a tunnel so vast that our entire observable universe, with all its hundreds of billions of galaxies, exists within its throat. In this model, the Big Bang was not an explosion in a pre-existing void. It was the moment one mouth of this primordial wormhole began to expand and cool, creating the space and time we inhabit. We are not living in a universe that contains wormholes, we are living inside one. This leads to a profound redefinition of what lies beyond our cosmic horizon. In the standard model, we can only see so far because light has had a finite time to travel since the Big Bang. But if we are inside a wormhole, then the boundary of our observable universe isn't a true edge, it's simply the throat of the tunnel leading to the other mouth. The Big Bang question finds a fascinating answer here. The other mouth of the wormhole could be connected to a completely different region of a higher dimensional bulk space, perhaps to another universe entirely or to a different epoch in a larger cosmic history. The Big Bang, then, was the moment this connection was established, the moment our cosmic tunnel opened for business. The immense energy and density we associate with the beginning would be the energy required to form and stabilize this gargantuan bridge between 2 points in the multiverse. The connection to a time loop emerges when we consider the ultimate fate of this wormhole universe. If the 2 mouths are connected not just in space but also in time, the entire structure could form a closed time-like curve. Imagine the wormhole not as a straight tunnel but as a U-shaped pipe. One mouth, our Big Bang, is the beginning of the pipe. The other mouth, which we might identify with the far future of our universe, perhaps its final collapse in a big crunch or even its heat death, is the other end. But if the pipe curves around in the higher dimensional bulk, that far future end could actually be connected back to the past. This would mean that if you could travel through the wormhole, you wouldn't just go to a different place, you would journey back to the beginning. The entire timeline of our cosmos, from bang to crunch, would be a single closed loop. The universe would have no true beginning or end because its end is spatially and temporally connected to its start. We are not on a linear timeline, but on a cosmic racetrack where the finish line is also the starting grid. This idea finds some grounding in the study of black holes. The interior of a black hole, according to the equations of general relativity, contains a singularity similar to the one at the Big Bang. Some physicists have speculated that the birth of a new universe could be connected to the formation of a black hole in a parent universe, with the black hole's interior expanding into its own spacetime continuum. The wormhole universe theory can be seen as an extension of this idea, but with a crucial difference. It proposes that the entire universe is the interior, not just a region spawned from a single black hole. This provides a potential mechanism for the wormhole's formation, a quantum gravitational process in a pre-existing meta-reality that pinched off a self-contained bubble of spacetime, connected back to its source by this cosmic umbilical cord. The theory elegantly blurs the line between the very large and the very small, suggesting that the universe itself may share a deep architectural kinship with the most exotic objects it contains. But a universe that is truly cyclical faces a monumental challenge, one that lies at the very heart of physics, the second law of thermodynamics and its relentless drive toward disorder. This law tells us that entropy, a measure of the universe's disorder, can only increase or stay the same over time. It's the reason why a shattered glass never spontaneously reassembles itself and why heat always flows from hot to cold. This gives us our familiar arrow of time, an irreversible direction from a past of lower entropy toward a future of higher entropy. So, if our universe is headed for a heat death, a state of maximum entropy where all energy is evenly distributed and no further work can be done, how could it possibly reboot for another cycle? A new Big Bang requires an incredibly low entropy starting point, a state of exquisite order. How do we get from the cosmic graveyard of maximum disorder back to the springtime of a new universe? This paradox is the central puzzle that any credible cyclical model must solve. The solution may lie not in violating the second law, but in redefining what we mean by a reset. One compelling idea is what we might call cosmic forgetfulness. Imagine writing a detailed message in the sand on a beach. Over time, the wind and waves slowly erode the letters, scrambling the information until all that's left is a smooth, featureless expanse. The sand is still there, but the specific, ordered message is gone. Its information has been lost to the environment. In a similar way, the transition from one cosmic cycle to the next might involve a process that so thoroughly scrambles the information content of the previous universe that entropy is effectively reset. It's not that the total entropy of the entire multi-cycle system decreases. Rather, the observable entropy from the perspective of the new cycle starts low again. The complex structures, the galaxies, stars, and planetary systems, are broken down into their most fundamental components. All the specific historical data, the intricate arrangements that constituted the universe's memory, are erased. The new cycle begins with a blank slate, a hot, dense, and incredibly uniform plasma. From this simple, undifferentiated state, the arrow of time can once again point forward, and entropy can begin its long, slow climb all over again. This concept connects deeply to the black hole information paradox we discussed earlier. If information is truly never destroyed, as quantum mechanics insists, then it must go somewhere. In a cosmological bounce like the one proposed in loop quantum cosmology, the information from the previous cycle isn't annihilated, it's thermalized. The immense temperatures and densities of the bounce act like a cosmic blender, pureeing all the complex structures of the old universe into a perfectly smooth, featureless soup of fundamental particles and radiation. While the quantum information is technically preserved in the correlations between particles, it becomes so hopelessly scrambled and delocalized that it is irrecoverable for all practical purposes. From the viewpoint of any emerging observer in the new cycle, the universe appears to have started in a state of very low entropy. The specific history is forgotten, but the essential ingredients for a new story are all present. Another perspective comes from the holographic principle. If our three-dimensional universe is a projection of information stored on a two-dimensional boundary, then a cosmic cycle could be a process of rewriting that boundary. The heat death of the universe would correspond to the cosmological horizon being filled to capacity with information, a complete but static record of everything that ever happened. A transition to a new cycle could then be seen as a reformatting of this cosmic hard drive. The information isn't destroyed, but it is re-encoded into a new, simpler state that serves as the initial conditions for a new Big Bang. The old data isn't lost, it's just rendered inactive, like a saved file on a computer that is no longer being used to run a program. The new universe runs on a fresh set of initial data, giving rise to a new arrow of time. In this way, the second law of thermodynamics is preserved across the entire multicycle timeline, while allowing for each individual universe to experience its own birth from a state of low entropy, a necessary condition for the emergence of the complexity and life that allows us to ponder these very mysteries. Sometimes the most profound clues about the universe's deepest secrets are hidden not in complex equations, but in simple numerical patterns. This brings us to a tantalizing idea that has intrigued physicists for nearly a century, proposed by one of the founders of quantum mechanics, Paul Dirac. It's called the large numbers hypothesis, and it points to a series of cosmic coincidences so staggering they seem to demand an explanation beyond mere chance. Dirac noticed that when you construct certain large, dimensionless numbers from the fundamental constants of nature, they are eerily similar despite describing phenomena on vastly different scales. For instance, consider the ratio of the electrostatic force to the gravitational force between a proton and an electron. This number is enormous, around 10 to the power of 39. Now consider the age of the universe expressed in terms of the time it takes light to cross an atomic nucleus. This, too, is a huge number, and it also comes out to be roughly 10 to the power of 39. Why should the strength of fundamental forces have any connection to the cosmic age of the entire universe? It's as if the microscopic world of atoms is in a silent, direct conversation with the large-scale cosmos. Dirac's radical proposal was that this wasn't a coincidence frozen in time. He suggested that these large numbers are related because the fundamental constants themselves are not truly constant. In his view, the strength of gravity might be very slowly weakening over cosmic time. If gravity weakens as the universe ages, then the ratio of the forces would change, and the apparent coincidence could be maintained if the age of the universe is similarly tied to this gradual change. This introduces a truly dynamic cosmos where the very rules of the game are subtly evolving. It's a vision of a living, breathing universe, not a static entity governed by immutable laws. For a cyclical model, this idea is pure gold. If the constants of nature can change over time within a single cycle, then what happens at the transition between cycles? Perhaps the constants don't just evolve smoothly, maybe they reset or are re-randomized with each new Big Bang. The fine-tuning we observe, the seemingly perfect calibration of constants that allows for our existence, wouldn't be a one-in-a-trillion miracle. It would be the result of an endless series of cosmic rolls of the dice. Over an infinite number of cycles, it becomes a statistical certainty that a universe with life-friendly constants will eventually appear. This provides an elegant alternative to the anthropic principle within a multiverse. Instead of an infinite number of parallel universes, each with different, random constants, we have a single, cyclical universe that gets endless chances to get it right. With each new cycle, the fundamental parameters are shuffled. Most cycles would be sterile, collapsing instantly or expanding too rapidly for atoms to form. But after a sufficient number of attempts, a combination like ours emerges, allowing for a long-lived, complex universe where creatures can arise to wonder at its beauty. The large numbers hypothesis, when woven into a cyclical framework, transforms the fine-tuning problem from a philosophical puzzle into a natural consequence of eternal return. We don't live in a uniquely designed cosmos. We live in a lucky one, the beneficiary of a cosmic process that has been running for eternity. The implications of evolving constants extend beyond mere explanation. If true, it would mean that the physics experiments we conduct today might not reveal eternal truths, but only a snapshot of the laws as they are in this particular epoch. The universe of 1 trillion years ago or 1 trillion years from now could operate under a slightly different set of rules. This idea connects Dirac's hypothesis to modern variations, like the theories of scalar tensor cosmology, which incorporate changing constants in a more rigorous mathematical framework. While precise laboratory measurements have so far placed very tight constraints on how much constants like the fine structure constant can change, the door isn't completely closed for variations over the immense timescales of a full cosmic cycle. The greatest legacy of Dirac's seemingly simple numerical observation is its power to suggest that our universe is far more dynamic and interconnected than we ever imagined, with its smallest parts and its grandest scale locked in a delicate, evolving dance that may well repeat itself forever. And so we arrive at our final contemplation, the 30th perspective on this grand mystery. After journeying through concepts from cosmic bounces and colliding brains to holographic resets and participatory universes, a compelling possibility emerges. The true mechanism behind a cosmological time loop may not be a single, elegant theory, but a symphony of them, a complex interplay where multiple principles converge to create the conditions for an eternal return. Imagine the universe not as a simple machine with one moving part, but as a vast, intricate clockwork where quantum gravity, holography, and multiverse dynamics all turn the gears in concert. Consider the possibility that loop quantum gravity provides the fundamental mechanics for a bounce, preventing a catastrophic singularity with its quantum repulsion. Yet, the information that defines our universe, the blueprint of every galaxy and every life form, is preserved not within the three-dimensional volume, but on a two-dimensional boundary, as the holographic principle suggests. This holographic data could be the stable substrate that carries the essential information through the violent transition of the bounce, ensuring that while the specific history is scrambled, the potential for complexity is reborn. Meanwhile, this entire cyclical process could be nested within the framework of eternal inflation, where our universe is just one bubble among an infinite multiverse. The multiverse provides the ultimate arena, an eternal background where the rare combination of physical laws necessary for a stable cycle can emerge through a form of cosmic natural selection. In this synthesis, the bounce is the engine, the hologram is the memory, and the multiverse is the breeding ground. This unified view helps resolve the most persistent challenges. The problem of entropy, the seemingly irreversible slide into disorder, finds a potential solution across this multi-layered system. While entropy increases relentlessly within our observable bubble, the holographic reformatting at the boundary and the quantum reset at the moment of the bounce could effectively create a new low-entropy starting point for the next cycle from our local perspective. The total entropy of the entire multiverse may continue to increase, but each individual universe gets a fresh start, a new arrow of time. This isn't a violation of the second law of thermodynamics, but a sophisticated consequence of a reality operating on multiple interconnected levels. Ultimately, this synthesis represents the very frontier of human knowledge. We are at a point where our most powerful tools, mathematics and sheer imagination, are straining to map the contours of a reality that may be far stranger than we can conceive. The search for the universe's first time loop is more than a technical puzzle. It is a fundamental inquiry into the nature of existence itself. It asks whether the cosmos is a one-off event or a perpetual entity, and in doing so, it reflects our own deep-seated curiosity about beginnings and endings. Whether the final answer lies in one of the theories we've explored or in a synthesis yet to be imagined, the journey has already transformed our understanding, revealing a cosmos of breathtaking grandeur and endless possibility, forever beckoning us to look deeper. We have journeyed across an astonishing landscape of ideas, from the elegant cosmic cycles of Roger Penrose to the violent rebirths within colliding brains, from the pixelated reality of causal-sets to the possibility that our entire existence is a simulation running on a cosmic computer. We've considered a universe born from a black hole, a cosmos that breathes in and out through quantum bounces, and even the mind-bending notion that our own consciousness might play a vital role in completing the loop of reality itself. These 30 theories are not just a list of possibilities, they represent the very frontier of human thought, a testament to our relentless drive to understand our place in the grand scheme of things. Each one pushes the boundaries of physics, philosophy, and imagination, challenging the linear narrative of time we hold so dear and replacing it with a vision of eternity that is both humbling and exhilarating. What becomes overwhelmingly clear from this exploration is that the question of a first-time loop is perhaps the wrong question to ask. In many of these models, the concept of a true beginning simply vanishes, replaced by an eternal process that has always been and will always be. Our search for a starting point may be a limitation of our own minds, which are wired to think in terms of cause and effect, of a definitive past and an open future. The universe, in its ultimate majesty, might operate on a logic far more profound, where time is a circle, a spiral, or an emergent property of a deeper, timeless reality. This journey forces us to confront the nature of existence itself, asking not just how the universe works, but why it exists at all, and whether the answer lies in an infinite cycle of creation and dissolution. The incredible diversity of these theories also highlights a crucial and exciting stage in science. We are in an era of magnificent speculation, where multiple compelling models compete for attention, each with its own strengths and mysteries. The ultimate test will come from observation from the faint whisper of primordial gravitational waves, the precise mapping of the cosmic microwave background, or a breakthrough in our understanding of quantum gravity. The true story of the cosmos will be written not by philosophy alone, but by the hard, testable predictions that these ideas make. This is the scientific process at its most vibrant, a collective human effort to peel back the layers of reality. Now we want to hear from you. This has been a journey through some of the most profound ideas ever conceived, and everyone has a favorite. Which of these 30 theories resonated most deeply with you? Does the holographic principle's vision of information-based rebirth capture your imagination? Or does the stark, quantum-powered spontaneity of a universe from nothing feel more compelling? Perhaps the elegant dance of colliding brains or the biological metaphor of cosmic natural selection speaks to you. Share your thoughts in the comments below. We are genuinely excited to continue this conversation with you. If this cosmic deep dive expanded your mind, please give the video a like, as it helps us explore more mysteries of the universe with you. And for more journeys to the edge of knowledge, make sure to subscribe and hit the notification bell. The universe is full of wonders, and the greatest mysteries are still waiting.